Shall we start the proceedings? Respected Registrar of VAT, Professor K. Narayanan, respected Director of the Texas Materials Institute and Material Science and Engineering Program at the University of Texas, Austin, Professor Armuga Mandiram, Dean of School of Advanced Sciences, VAT, Professor A. Mary Saral, eminent speakers from abroad, faculty colleagues from VAT and other institutes, and student participants. Very good morning to you all. On behalf of VAT management, faculty members of School of Advanced Sciences, and conference organizing committee, it is indeed a great pleasure and honor for me to welcome you all to this international virtual conference on high performance materials for energy, environment, and healthcare in the digital era, organized by Center for Materials Technology, School of Advanced Sciences, VAT. I'm sure that on these 2 days of conference, we will hear from the best minds from the world and enrich our knowledge. Once again, I welcome you all to this conference. Now I request Professor Emery Saral, Dean of School of Advanced Sciences and Convener, to speak about the conference.
Thank you very much, sir. Respected Registrar, honorable speakers and scientists from various parts of the world, professors and students across the globe, and my dear VITians, very good morning, good afternoon, good evening, and good day to all of you. Indeed, it is my pleasure to welcome you and address all of you who have come forward to spend your valuable time with us in spite of this pandemic situation. I invite all of you for this 2-day international virtual conference on high performance material for energy and environment and healthcare in the digital era. I am proud and privileged to introduce the new Center for Materials and Technology, which is abbreviated as CMT, which will function under School of Advanced Sciences, focusing on energy, conservation, harvesting devices, flexible voltaics, electronics, piezoelectric and piezosensitive sensors, thermoelectric power generators, environmental and health monitoring devices, which have been already given as the theme area of this conference. It is my pleasure to inform you that this is a new center which is established from School of Advanced Sciences. At present, it comprises of the eminent scientists from Physics and Chemistry department, and later on, we are thinking of expanding this center involving all the professors across the university. At this juncture, it is my pleasure to invite all the speakers. So as it was introduced in the welcome note, we are going to have around 10 speakers from across the country. And one of the important speakers is Professor Armuga Mandiram, who is the Cochlear Family Regents Chair in Engineering, Director of both Texas Material Institute and Material Science and Engineering Program at the University of Texas, Asst in USA. He worked with Professor John Goodenough, who is the Nobel Laureate in Chemistry in the year 2019 in Oxford University, Asst. It is noteworthy that Professor Armuga Mandiram delivered the 2019 Chemistry Nobel Prize lecture on behalf of Professor John Goodenough in Stockholm. In this conference, I am very much privileged and glad to share with you that we are going to have 4 renowned professors and researchers from abroad who have consented to give the address, and then we are going to have about 1,800 faculty and students from VIT and other institutions participating in this conference. So I welcome all the speakers, and also I'm very much thankful to all the speakers for having consented to address our platform, who is going to have various participants across the globe. Thank you very much, professors, as well as the speakers. And also it is my pleasure and privilege to introduce about the School of Advanced Sciences, which comprises of Department of Chemistry, Physics, and Mathematics. At this juncture, it is my pleasure to share with you all that the Department of Chemistry from School of Advanced Sciences from VIT University has been ranked in the University QS World Ranking for the subject in the year 2020 with the ranking of 451 to 500. And within India, we have been ranked in 16. And also, I am privileged to share with you that it is one of the best universities for subject chemistry. And also, we have been ranked in 433 and in India by 15 with the subject score of 43.7 by Clarivate analysis. We have about 236 in the School of Advanced Sciences, and I'm happy to share that all the faculty colleagues are PhDs, and most of them are from premier institutes in India like IIT, IISc, and other institutes. And faculty members with PhD degree from abroad, China, and France. More than 100 faculty are with PDF international exposure from the countries like USA, Japan, Taiwan, Germany, Israel, France, Korea, and Singapore. We have started the department in the year 1984 with a humble beginning of Department of Physics, Chemistry, and Mathematics. And we are offering right now 5 important programs, PG programs with the school. We are offering MSc Chemistry, MSc Physics, MSc Data Science, and 5-year integrated course on computational statistics and data analytics. In addition to that, this year we are planning to offer MSc Business Statistics by the Department of Mathematics. And also, I am very much privileged to share with you all that the MSc Chemistry course is going to be accredited with Royal Society of Chemistry, and also the department plan to offer 1+1 courses with foreign university collaboration in the coming years. And also it is worthy of mentioning here that the Department of Chemistry and other departments with School of Advanced Sciences have established major research facilities, which is funded by VIT. We have TEM, and also we have the upcoming facility, high resolution mass spectrometer. I am also very much pleasure to share with you that the Department of Physics and Chemistry have been recognized by DST FIST in the past as well as in this year. By 2020, we have been granted with 2.2 crores to purchase single crystal to establish the single crystal XRD facility, and also 2.65 crores to establish the VSM facility for the Department of Physics. So it's my pleasure to tell you that the Physics and Chemistry department along with Maths department, the school is leading the university in terms of collaboration, in terms of funded projects, and also we are good in publishing in good Scopus Index journals with good impact factor. So with this a few glimpses of the School of Advanced Sciences, I invite you all for this international conference. I suppose this forum will be a very useful forum for all of you to understand what is happening in materials technology involving nanotechnology. And I wish you all the best and happy learning in this online platform. At this juncture, I would like to express my sincere thanks to our esteemed management for providing all necessary guidelines and also the support to establish the new center and also our research to excel in all aspects. So I am very much thankful to our registrar who have consented to give the inaugural address now. And I would like to thank you all for your listening in this online platform. Wish you all the best. Thank you.
Thank you, ma'am. Now I invite Professor K. Satyanarayanan, Registrar of VIT, to address the audience, please.
Good morning to all. I am very happy to note that School of Advanced Sciences, Vellore Institute of Technology is organizing the International Virtual Conference on High Performance Materials for Energy, Environment and Healthcare in the Digital Era through its newly born center, namely Center for Materials Technology. I am also equally happy to note that the conference is going to be addressed by great scientists like Professor Armugam Mandaram and a galaxy of other scientists. In the coming years, rather I will say in the coming decades, we are going to see a large improvement in our knowledge of electrochemistry, electronics, sensors, environmental science, and healthcare. Chemistry, especially material, is going to be the center of these great improvements. Even though our country is improving a lot, but we are lagging in scientific inventions. When I say computer, an average Indian will think of software, but citizens of developed countries will think of hardware. That is the major difference. If we have to really improve, we have to concentrate on hardware and our country will see the real development when it comes true. All these hardware technologies are revolving around materials, whether it is inorganic material or organic material. The areas like batteries and solar cells, that is, as per the existing knowledge, they are mainly depending on inorganic materials, but sensors, OLEDs, organic lasers are the developing areas in organic materials. Our institute and department, already told by our dean, it has grown from a humble beginning to this level within a period of 20 years, even though the institute is 36 years old. According to QS ranking, again as our dean told, chemistry department is placed in the bracket of 450 to 500 in the world, and I will proudly say this is the only private technological institute in our country where chemistry is entered QS world ranking. I hope we will have a good number of publications from our department in high impact factor journals in the near future. I thank School of Advanced Sciences and the organizers to organize this conference at the time of pandemic in the country. I hope we will have many thought-provoking and idea-giving lectures today and tomorrow. Thank you.
Thank you, sir, for your impressive address. Now I request Dr. Samir Ranjan Meher, member, organizing committee of the conference, to say vote of thanks.
Thank you, Dr. Cheralathan, honorable dignitaries, most valued guests, and dear participants. Good morning to all of you. It is my pleasure and privilege to propose the vote of thanks on behalf of the organizing committee. At the outset, we would like to thank the VIT management for their constant support and encouragement to establish the Center for Materials Technology under the School of Advanced Sciences and to organize this international virtual conference during its budding stage. We would like to express our heartfelt gratitude towards our respected Vice Chancellor, Dr. Anand A. Samuel, and Pro Vice Chancellor, Dr. S. Narayanan, for being the constant guiding force. I extend our sincere thanks to our Registrar, Dr. K. Satyanarayanan, for felicitating the chief guest and the invited speakers. We express our deep gratitude to the Honorable Chief Guest, Dr. Armugam Mandiram from University of Texas, Austin, who has spared his precious time for us and graced this occasion with his web presence. We would like to thank all the invited speakers, Dr. Srikanth from University of South Florida, Dr. Kim Hong-du from Kyung Hee University, Dr. Palani Balaya from NUS Singapore, Dr. Sudagar from Swansea University, United Kingdom, Dr. Muhammad Lukman from Taiba University, Saudi Arabia, Dr. Srinath Subramaniam from Institute of Bioecoscience, Maryland, USA, Dr. Muhammad Fatlala from University of Cape Town, Dr. Nihar from Jackson State University, USA, Dr. Hong Sing Bom from KAIST, Republic of Korea, Dr. Just Rick from University of Amsterdam, Netherlands, and Dr. Mario Caironi from Italian Institute of Technology for sharing their cutting-edge research experience. A warm thanks goes to the convener and the Dean of the School of Advanced Sciences, Dr. A. Mary Saral, for being the backbone of this international conference. We would like to thank the organizing secretary, Dr. Cheralathan, for his tireless efforts to make this virtual conference a grand success. Special thanks to Dr. R. Vijayaraghavan and Dr. A. Senthil Kumar for constantly guiding and motivating us during each and every step. I would like to acknowledge the manifold attempts of our committed faculty coordinators, Dr. Anand Prabu, Dr. Dhritiman Gupta, Dr. K. Vasu, Dr. Ganesh Babu, Dr. Raja Sekar, and Dr. Charles. We would like to thank the VIT CTS team for providing the technical logistics. Last but not the least, we are grateful to all the participants, both from academia and industry, for their overwhelming response. We hope that the conference will be fruitful to all of you. Thank you.
Thank you, Dr. Samir. This is
You can I start with that Cheralathan or will mention?
Thank you, Dr. Samir. This is the end of introductory session. Now let us move on to the technical sessions. The technical session will start exactly at 9:45 a.m.
Hello, good morning.
Good morning, sir.
Can you allow me to share my screen?
Yeah.
Sir.
Yeah. Yes, sir. I
Sir.
will
Sir, before sharing the screen, there'll be a slide to introduce you. After that, please share it, sir.
Okay.
But
Let me see my screen shares now. Let me see.
Yes, sir.
Can you see my screen?
Yes, sir. Good morning, sir.
Do you see my screen now?
Yes,
Yes,
sir.
sir.
We can see your screen. Yes, sir. Good morning, sir.
Let me put the whole full screen to make sure it works. Do you see the full screen?
Yeah, now.
Yes, sir. We can see your full screen. Good morning, sir. I would like to request you to stop sharing because we have the introductory slide about you. Yes, sir. Yeah.
I just wanted to make sure it works.
Okay. Okay, sir. Thank you so much, sir.
Okay. Is my volume okay, or you want me to increase the volume?
Audible, sir.
Okay.
Sir, we very well hear you.
Okay. Thank you. Okay.
Yes, Cheralathan, sir. You can share the introductory slide about sir. Yes, sir. Over to Vijayaraghavan, sir.
Good day to all delegates. Thanks to Registrar Sir and Dean Ma'am for setting the stage for the center. And it's my pleasure to welcome the two speakers for the first session number 1. We have two eminent speakers, both are from USA, but both are Indian origin. The first speaker is Professor R. Mandiram from the University of Texas at Austin. Before I go to the introductory part, just a few guidelines on the logistics. We have 45 minutes total. 30 minutes, it's 30 plus minutes for the lecture, plus question answer session, plus for connectivity, we have some buffer time as well. So the opening lecture is by Professor R. Mandiram from the University of Texas at Austin. It is most appropriate that Professor Mandiram inaugurates the scientific session with our visual conference on energy and environment as a plenary lecture. For the benefit of the audience, I would like to introduce Professor Mandiram briefly. He is a scientist turned into a technologist to deliver the products in the era of rechargeable world and mobile world to develop lithium batteries and so many materials. His credentials are shown here. He had his early education at IIT Madras, PhD. He worked on modern bauxite. Later, he went on to make metals with very many materials, and then for products. And then he worked with Professor Goodenough at Oxford. Later, he moved to the Texas. Then Goodenough also moved to the Texas at Austin. We worked with him for so many years. He had his own group as well. He collaborates and associates with Professor Goodenough as well. And he's a faculty member at the Department of Mechanical Engineering from 2001. Then he's the director of the center now. He's also a chair professor and it's called this doctoral chair professor. And he has got a lot of awards and recognition, as you can see. He is also ECS member, and he delivered the 2019 Chemistry Nobel Prize on behalf of Professor Goodenough in Stockholm to develop the Ion batteries. And he is a honorary mechanical engineer of the ME Academy of Distinguished Alumni Award, Distinguished Alumnus Award of IIT Madras, select member of the Third World of Academy of Sciences. He is a Web of Science, highly selected researchers in the year 2017 to 2019, continuously for 3 years. He has got over 800 scientific papers, the H index of 126. Currently, he has got 30 PhD students. And briefly to say, he started on with molten oxide, then worked on many oxides and solid state and metals chemistry problems, thermoelectric superconductors to enhance the understanding of structure, property, performance of materials. His current interests are rechargeable batteries, fuel cells, solar cells, supercapacitors. It is with immense pleasure that I invite Professor Armugam Mandiram to deliver his plenary lecture. Sir, please.
Okay, let me share the screen. Can you see the screen?
Yes, sir.
Okay. Good morning, and thank you for the long introduction. Happy to be here tonight or morning for you to say a little bit about what we have been doing here at the University of Texas at Austin. So my title is Battery Technologies for a Cleaner Environment. So energy is a central societal issue. It impacts our way of life, economy, national security, and environment. This here on the left gives you the global energy consumption as we move forward. As you see here, the energy use is skyrocketing, and it is expected to triple by the year 2100 based on moderate economic and population growth. And right now, the energy use is dominated by fossil fuels, and that has two issues. Finite supply, and then it causes a lot of air pollution, global warming, and air pollution, health issues. So based on all those, I would say energy is one of the greatest challenges facing humankind in the 21st century. I've also given here comparing 3 countries, United States, India, and China. The numbers here in red are population in those 3 countries. If you see China and India, we have similar population. I think the population in India may be actually more than in China, but at least these are the numbers, kind of, you can assume we are similar. But if you look at the energy use, even though China and India have similar population, the total global energy use is 23% by China, India only 5%. So if you assume that the lifestyle or whatever going on in China, if India becomes similar to that, we will be needing at least 4.5 times more energy than what we use now. Then if you take US, the total energy use is 17%, but the population is 1/4 of the population of China and India. So if our lifestyle in India becomes similar to US, then you can imagine we will need 10 to 15 times more energy than what India uses now. So why I am saying this, as we move forward, energy is going to be a critical challenge for India, and then something needs to be done to take care of this problem. Right now, we are all having the COVID-19 epidemic, but it is temporary. I hope some vaccine our proper medication will come out, and we will all be relieved. But energy is not going to be like that. It is going to be there forever. So we need to find solutions so that we can have a sustainable life. So this chart is this figure is from Smalley Institute, Rice University in Houston. So it gives the humanity's top 10 problems for the next 50 years. You see, number one problem is energy. It's on the top. Number two problem, water. Actually, for India, both energy and water are critical problems. For me, this is like a chain reaction. You have a lot of chemistry centric. The conference seems to be chemistry centric. So you all know chain reaction. So what I mean by that is, if you have problem with the energy and water, that is going to create problem for food. If you have problem for the first three, that is going to cause lot of problem for the environment, pollution. And if you have problem for the first four, then that is going to create poverty. If poverty is going on, everybody will become restless. There could be terrorism, there could be war. If it is, there will be diseases. And then all the education will be lost because everything will be crazy. If education is lost, democracy will be gone. If democracy gone, if all these problems happen, actually population may go down. So you can see energy is going to be, or it's already beginning to be, but it is going to become more and more challenging as we move forward. So what is the solution? The solution is renewable energy. Nobody wants it. It's available in plenty everywhere. Solar energy and wind energy. But unfortunately, they are intermittent, meaning solar energy comes only in the daytime and when it is not cloudy. Same way, wind blows when it wants to blow. So what can we do to collect electricity from these renewable sources, store them, and use them efficiently and economically? For storing, batteries are the most probable or most viable option. Supercapacitors as well, but supercapacitors are similar to batteries. They will store much less energy compared to batteries. That's why all the action is on batteries worldwide right now. Right now, the storage is the bottleneck to use renewable energies. All sounds nice. Solar and wind energies are available. Battery technologies are also there. So what is the problem? The problem is cost. That's the major problem. How much energy you can store, how fast you can charge, what kind of durability, life you will have with the battery, and are there going to be safety problems? So we need to tackle all this, and they are all linked to severe materials challenges. And you'll hear a little bit more as we move forward. In addition to that, our lifestyle has changed a lot. When I was a student, or a kid, I would say, child, I was born in a very small village, 40 houses. So I used to walk 2 miles, that is 3+ kilometers, one way, just by walk. Now it is not like that. The lifestyle has changed everywhere. So in the US, for example, or even in India, you just get out of the garage, in your car, go to work, then you get back to home without much walking. So a lot of transportation, and it is keep going up in India, walking to bicycle, to two-wheeler, to car. So that's how it is going. So for transportation, there are not a lot of options. Batteries are the only viable near-term option. So that's why, again, both for stationary storage of electricity produced from renewable energies, as well as for transportation. Batteries are very, very critical. Not only that, right now we have power plants using fossil fuel, and those power plants have to be operated it is demand based. They have to be scaled up or scaled down depending upon the need. What do I mean by that? In the daytime, we use a lot of energy, so you have to do too much. In the daytime, less energy is used, so we do less. So that is not efficient way of operating the power plants. If you have good storage system, you can operate them at a constant level, and any energy, excess energy you produce during the night can be stored, and that excess energy can be used during the daytime. Again, batteries are the most viable option to do that. So it's not only for using renewable energies, but also for efficiently operating the current conventional power plants. Sounds nice and good. What is the problem? The problems are cost again, then energy density, that means how much energy you can store in a given size or volume or in a given weight. How fast you can charge and discharge, power density. How long I can use it before I have to change my battery. Are they safe, or am I going to create problem when I am on the road? If I use this technology, am I going to create more environmental problems than I have now? All of these contribute to cost. Cost is not just raw material alone. If I store more energy, instead of making 100 batteries, I can make 50 batteries. So that is saving money. If my battery works for a long time, I do not have to replace it. That reduces my overall cost. If it is safe, I do not have to worry too much. That saves money. If it is environmentally benign, I do not have to worry about. In the US, for example, we have something called Environmental Protection Agency. So you do not have to worry about that. So everything contributes to cost. In addition to these 6 parameters, we should also worry about operating temperature. In South India, hot, and even in Delhi, summer, very hot. So you should be able to operate the battery at 50, 60 degrees C. The same way, winter it can become cold, particularly in the north in India, near Himalayas specifically. So your battery should be able to operate both high temperature as well as low temperature. In addition to that, it will be nice if I can charge the battery fast, maybe 10 minutes, so that while I am driving, when I go to bathroom, in 10 minutes, if I can get it charged, when I come out, or when I sit and eat in a restaurant for 15 minutes, drink coffee, if this can be charged in 5-10 minutes, I'm ready to go. So it's very complicated, but all of these depend on only 2 things: chemistry and physics, which material we use and what kind of structure where they have and how their bands, energies are aligned related to each other. All those things are related to intrinsic chemistry and physics. And then all these parameters, too many parameters, which parameters I have to worry about, or which battery technology I can think of for a particular application. All those depend upon the application actually you want to use. For example, portable electronic devices, cell phone or laptop, energy density is the most important issue. How long I can use it before I have to charge it. The life is not very critical. Many people change phone in 3 years, 4 years, or 5 years. Same way laptop becomes obsolete, you change in few years. So energy density is the most important issue. When you go from portable devices to electric vehicle, yes, energy density is still important because I want to drive long enough distance before I have to charge, particularly in developing countries, like in developed countries, like in the US. But in India, for example, the driving distance is not very critical because a lot of people drive shorter distance. So for India, the criteria we have to use are slightly different. Temperature tolerance is very important. Fast charge is very important for India. It's important for everybody, but particularly for India, those are more important compared to the energy density itself. But now, coming to my point, when I go from portable devices to electric vehicle, still energy density is important, but I have to also worry about the cost. Why? That car battery is going to be much bigger, more expensive, $10,000–$15,000, not like cell phone battery, so cost comes into picture. I need to worry about safety as well. Larger battery, I'm on the road. I don't want to create problem to the cars behind me or before me or on the sides. Life is important as well. When you go to grid storage of electricity produced from solar and wind, cost is the major issue because that battery is going to be very large, and reliability, how reliably I can get power or use the storage system to get electricity, because it is going to power the whole Chennai city or whole Bangalore or Delhi. So reliability is important. How long I can use is important because you want to use it for 10–20 years before you have to replace it. How fast I can recharge is important, and safety is important. Energy density is also important, but not that critical because you have a lot of land. Of course, if you store more energy, instead of making 50 batteries, you can make 25 batteries. So you save cost, right? So everything is cost. So that means we should not be thinking that there is one glorious technology that can be used for all of it. Particularly for grid storage, maybe something different than lithium ion batteries may be more probable because of cost considerations, and only time will tell. And I can assure you, it is not going to be just only one technology which is going to be used all over the world. It may be different battery technologies for different applications, as well as for different countries and maybe different regions in a specific country. So all those needs to be seen. We have to wait and see. Now to the science. How does a lithium ion battery work? The lithium ion battery any battery will have three components: a negative electrode called anode, a positive electrode called cathode, and they are separated by an electrolyte, and that electrolyte should be electrically insulating. It should not allow electrons to pass through. If it is, you will be internally shorting the cell. So electrolyte should allow charge transfer between the two electrodes only in the form of ions. In this case, we are transferring positive charge between these two electrodes in the form of lithium ions. Whereas the electron should go through the external circuit. So that could be a copper wire that should allow only the electron to go through, not the lithium to go through. So if you think of it, it's very nice. I have two electrodes here separated by an electrolyte. When it operates, when you charge it, for example, lithium ions go from the cathode to the anode. During discharge, exactly the opposite happens. So when you charge it, so that is what is happening. Lithium ions are flowing internally between the two electrodes during charge and discharge. Electrons are flowing externally through the external circuit between the two electrodes, doing the useful work for us during that process. Now, during this process, during charge, you are putting electron from the energy levels or energy band of the cathode and putting it into the anode during charge. During discharge, you are pulling electrons from a higher lying energy in the negative electrode and putting into a lower lying energy band in the positive electrode. So that energy difference between these two, because the electrons are falling when you use the cell phone or drive the car, the electrons are falling from this higher energy anode level to a lower energy level in the cathode. So the energy released out is used as electricity. So that's how the battery works. So what all you do is you use your electrical circuit, plug it in, and use that electricity to pump the electron from this level to that level during charge, and you store it, the electrical energy in the form of chemical energy, and during use, you take that chemical energy out as electricity. So that's how it works. Now, in the traditional lithium-ion battery, anode is graphite that has its layered structure, and the cathode is lithium cobalt oxide. So that's the cathode. It's going back and forth between two nice layered structures. But it need not be exactly layered. Other structures are possible. But I don't have time to go through all details. At least you know how a battery works, and you should all be happy. It is all because of the chemistry and physics this engineering technology has become possible. Now, why lithium-ion batteries? Why not something else? Of course, I have lead-acid battery in my car. Every vehicle has that. Nickel cadmium, nickel metal hydride. Why are we using this? The reason is this. All these batteries, lead acid, nickel cadmium, nickel metal hydride, they all use aqueous electrolyte. That means water-based electrolyte. Lead acid, sulfuric acid. The other two uses KOH. So everything has water. When you see these energy levels, you see your anode negative energy level is here, positive electrode energy level is here, and they have to lie within the band gap of the electrolyte. Remember, the electrolyte is in between the two electrodes, and that has its own highest occupied molecular orbital filled and lowest unoccupied molecular orbital empty. So these two levels, cathode and anode, have to lie ideally within that band gap. If not, supposing if this level lies above here, when I charge it, I will pull the electron from here and put it over here rather than here, because this is the lower lying level if this level is somewhere here. You see, so you will be internally leaking electron between the two electrodes if these things lie outside. So that's a constraint. Electrolyte is a constraint to determine the difference in energy between the cathode and anode. So energy density is the user time, how long I can use it. That depends upon two parameters. Cell voltage times amount of charge I can store in these two materials. In this case, lithium ions. How much lithium ion I can store in a given weight or given volume in these two materials. That's this. Cell voltage is the difference in energy between the negative electrode and the positive electrode. So, if you want to use your battery longer, before you have to charge it, this has to be as low as possible. The anode level has to be as high as possible. But the electrolyte is constraining them. I cannot keep on raising that. If I raise too much above LUMO, then I'm going to have a problem, instability. Same way, if this goes below the HOMO, there will be electrolyte instability. You see, electrolyte is constraining the energy difference you can really make use of between these two electrodes. So in these batteries, lead acid and all water-based, this band gap is smaller. So that means the difference in energy between the negative electrode and positive electrode is smaller. You use materials in such a way that that energy difference is smaller, or in other words, the voltage is less than 2 volt. Lithium-ion batteries use non-aqueous electrolytes, so the band gap is larger. So this is lower, that is higher. So we can get at least around 4 volt from a lithium-ion cell. That is why all the action is on lithium-ion cell. You get longer user time before you have to recharge it. Now there are 3 components. Among them, the cathode is the most expensive one because it uses cobalt. Cobalt is not abundant, and because of that, 50% of the materials cost in the battery, lithium-ion battery, comes from the cathode. And cathode also limits the amount of charge you can store compared to the anode. Cathode also limits the operating voltage less than 4.3 volt. So cathode is at the center of attention in the battery community. So fortunately, we do a lot of work in the cathode area because that is just transition metal oxide chemistry, and that's what I did my PhD. And I was fortunate enough to work with Professor Goodenough, both at Oxford as well as at University of Texas at Austin. So that has been very valuable over the time. Now, lithium-ion batteries are not the only one. There are so many batteries. I explained the concept. Similar concepts can be applied to a lot of other systems. So these are all, a lot of them are working ion based. Here the working ion is lithium ion. Like I said, lithium ions are moving back and forth. That is lithium ion. Supposing sodium ions are moving back and forth, that is sodium ion battery. Calcium ions are moving back and forth, that is calcium ion battery. So you can think of all these. These are all various possible batteries. I already explained lithium-ion batteries. Sodium-ion batteries can be similar to lithium-ion, excepting you use a sodium-ion conducting electrolyte and your working ion is sodium-ion. But sodium is a little bit heavier than lithium. So we'll always get a little bit less energy density with the sodium-ion batteries compared to lithium-ion batteries. But sodium-ion battery brings one important advantage. What is the advantage? Sodium is available plenty everywhere in the ocean. Nobody owns it. There is no monopoly. So that gives a lot of advantages, particularly for grid storage. Magnesium 2+, zinc 2+, calcium 2+, aluminum 3+. You see, I mentioned to you, the energy density also depends upon the amount of charge stored in the form of ions. If it is lithium or sodium or potassium, if I store one ion, I store only 1 plus charge. If it is calcium, magnesium or zinc, if I store one ion, I store 2 charges, double. If it is aluminum ion, I can store 3 charges. So my energy density suddenly goes up. But when you go from lithium to sodium, the voltage will decrease. Sodium to magnesium or zinc, the voltage will decrease. Yes, you will increase this quantity, but when you go from lithium ion to other things, cell voltage will decrease. So at the end of the day, see, during this process, these ions are also moving in this crystal lattice. If you have zinc ion or magnesium ion or aluminum 3+ ion moving, there will be a lot of electrostatic repulsion between the positive ions present in these materials and the working moving ion zinc 2+ or aluminum 3+. So diffusion is going to become a big problem. So at the end of the day, even though it's very, very nice, I can store more charge, the diffusion becomes a problem, voltage will go down. So if you ask me, I do not believe practically, in a practical cell, we will get higher energy density with any of these compared to lithium-ion batteries. Of course, they will give a much better cost advantage like calcium or zinc or aluminum. So cost advantage will be there, but energy density advantage, apparently it may look, but practically we may not get. All these, even this one I explained, uses lithium cobalt oxide or something. They are metal oxides, metal based or metal sulfide. If you use a metal sulfur battery like lithium sulfur or sodium sulfur, they don't use metal based materials. Sulfur is a byproduct in the petroleum industry. So it is also available plenty, environmentally benign, lot of advantages, but there are many challenges with sulfur based batteries. If you go to magnesium, calcium, aluminum, again there will be a lot of diffusion problem, but with lithium and sodium, there are some diffusion problem, dissolution problem, not a problem, but continuous progress is being made. You see, there are possibilities. The metal-based batteries may be thrown away. Something like this could be used, or even organic-based batteries. Plenty of different opportunities. Metal air batteries, non-aqueous, forget about it, very hard. But aqueous batteries, metal air, zinc air battery, possible for grid storage. So redox flow batteries means here most of these batteries use solid electrodes, liquid electrolyte. Redox flow, you use liquid chemicals as electrode. So you flow, so you can store really the chemical in a tank. So that is mainly for grid storage, not for car or portable devices. All solid state, that is the holy grail. Use solid electrolyte, solid electrode, no leakage, much better safety. But if you have two solids together like this, the charge transfer between the electrode and the electrolyte is going to be hard. So rate how fast you can charge, discharge can go down. And also, how are you going to manufacture large area solid electrolyte with good mechanical properties? That's a big issue. So a lot of work is being carried out. We have to wait and see how things come out. But right now, there is nothing to beat lithium ion technology. That's why everything is happening around that. Now, we all use it. How did it all happen? Three people. They are our heroes. So they got the Nobel Prize in 2019 in chemistry. Professor Stanley Whittingham in the United States. He was actually a PhD student at Oxford, but he moved to the United States and he worked at Exxon Corporation, oil company, petroleum company. So in 1976, he demonstrated the first rechargeable lithium battery by having a lithium metal electrode anode and a TiS2 cathode. So that can give less than 2.5 volt because you cannot have cathodes below the top of the sulfur 3p band in a sulfide. Lot of work was happening. People were trying to commercialize, but lithium metal posed a safety problem, so they were pulled out of the market. Good enough, started his career in the early 1950s. So he had lot of wealth of knowledge on oxides. When I was doing PhD in India, we used to call him the father of solid state chemistry. So with all the oxide knowledge he had, he knew where the oxygen 2p band is, where the sulfur 3p band is, and he was able to recognize that he can have the cathode energy at a much lower level than that if he is using a sulfide. So that's how lithium cobalt oxide, lithium nickel oxide formed. And if you couple that with the lithium metal, you can suddenly get 4 volt as opposed to less than 2.5 volt with TiS2. Then Akira Shishima, he came, he coupled the cathode, the lithium cobalt cathode, oxide cathode, and the graphite anode, and demonstrated the first lithium ion cell. So that's how the whole technology we are using became possible. So that's why the Nobel Prize were given these three distinguished scientists. Now I mentioned in the battery, cathode is the most expensive. There are 3 possible cathodes: layered oxides, phenol oxide, and polyanion oxide. All of them were discovered by Professor John Goodenough's group, involving 3 visiting scientists from 3 different parts of the world. They were not students. They were visiting scientists, came to work from 3 different parts of the world to Oxford. Mishishima came from Japan, worked with Professor Goodenough. They developed the layered lithium cobalt oxide, lithium nickel oxide. That's the very first oxide cathode demonstrated. He left. Michael Thackeray came from South Africa. He worked on spinel LiMn 204. He left. I did my PhD in India. I worked both at IIT Madras and IIT Bangalore. I went to Professor Goodenough in 1986. So my PhD dissertation or thesis was on molybdenum oxides. So with that, I started working with him as a postdoc or visiting scientist on a series of iron containing polyanion compounds, meaning iron molybdate, iron tungstate. So when we do this, iron molybdate gave 3 volt. Fe2O3, if you do, it will be less than 2.5 volt. So that was a surprise. Same iron 2 plus 3 plus coupled, why are we getting more voltage? As soon as you change molybdenum to sulfur, you get 3.6 volt instead of 3 volt. So that is where the so-called inductive effect in 1987-89 was found. So that is the third series. So the 3 cathode series were developed solely by only one group, Professor Goodenough group, both at Oxford, these 2 at Oxford. This one started at Oxford, but published from UT Austin, University of Texas at Austin. So that's how still these are the 3 practically viable cathode systems even 30 years later. All others are kind of playing around this unless sulfur or something else comes into picture. So that's the history. Now, I think my time is running out. I won't have too much time. I'll take a couple of minutes probably. There is rich chemistry. After my PhD, I was actually, everybody will go from IIT Bangalore or IIT directly to US, but I was not fortunate enough at that time. Something happened. So I was working in India in a small college. I was teaching. Whatever I was teaching in inorganic chemistry in that college was very, very helpful. Even today, whatever I am doing in research. So these are the materials used right now. Nickel, manganese, cobalt oxide having this kind of formula, rich solid state chemistry. So the education I had on oxide chemistry in India, as well as the teaching, that is very, very still useful on many things I do. So I want to tell one thing to students and even for faculty, teaching and research are inseparable. If you do good research, you can be a good teacher. If you are a good teacher, you can be a good researcher. So they go hand in hand. That's the way we have to look at it. Now, with this material we are making with a tank reactor, we can synthesize real good material. So our objective is to eliminate cobalt. So I will directly go there. We have eliminated cobalt. It is a big concern. And that paper is going to come out. This is the very, very first paper completely eliminating cobalt, showing 1000 cycles. So we can make lithium ion batteries without using the expensive or less abundant cobalt. Graphite creates a lot of safety problem. So we have been working on a foil anode that can allow fast charge, safer than the current technology, cost low as well. So that is another technology we are working. All chemistry again, like interdigitated electric alloys like this. So that can be made as a foil with inexpensive process. Sulfur stores 10 times more energy than lithium cobalt oxide, but poor electronic conductor, poor ionic conductor. Polysulfides are formed intermediate. It goes from one electrode to another electrode, messing around. It's a big problem. What people do, throw a lot of electrolyte, throw a lot of carbon. So that is not going to make the practical cells. So we are very much focusing on controlling all these parameters so that the lithium sulfur technology can be made practically viable. This is the last technology for grid storage, flow system or half flow. This side may be solid electrode or liquid electrode. This side you can use air or bromine, potassium ferrocyanide or quinone. Lots of possibilities in flow battery. The crossover is a problem, so we try to use a solid electrolyte. This is mainly for grid storage. Again, lot of chemistry involved here. Conclusion, I don't have to explain too much about the importance of lithium-ion batteries. They have revolutionized the portable electronics, beginning to transform the transportation sector. They have the potential to penetrate the utility industry. Right now, this is the level 250 watt-hour per kilogram, but by changing the electrode materials, we can get other values or higher values. This is my group. Around 250 people have worked with me over the years, postdocs and students. They are all over the world. About 45 of them are faculty members around the world, including a couple of them in India. So I'm very, very grateful to all the people. This is my current group. All the people who have worked with me during the past 30 plus years. That made my job enjoyable. I'm also grateful to the funding agencies, particularly the Department of Energy. Thank you. I think I took 4 minutes more. Thank you very much.
Thank you very much, Professor, for giving an overview from the basics to the advanced and then to the products. There are 3, 4, 5 questions that on behalf of the audience, I would put forth to you.
Okay.
Yeah, please. Can I go ahead, sir? First question is on the future of lithium-ion batteries. Probably they want to know about the environmental concern or the refurbishing aspects.
Okay, so lithium-ion batteries are going to be there no matter what, because of a lot of advantages, but slowly cobalt will be eliminated. I think nickel will be there. Without nickel, it's very hard to use. So we can make batteries without any cobalt, or we can find other materials analogous to lithium-ion, lithium sulfur. If that can work, it is similar to lithium-ion, excepting you try to use lithium metal. In fact, if you use Li2S, then it will be like a lithium-ion battery. So it is going to be there. As we move forward, recycling is very, very important. Even though we can get rid of cobalt, nickel will be still there. You have to recycle and use it. And also used batteries, we can do something to make use of them. So those are not happening very much, but if you have a lot of car batteries and grid storage batteries, there will be a lot of work happening, a lot of funding there, so it will happen. So it is going to be there, but modifications will be slowly happening.
Thank you, sir. Next one is how about ionic liquids in place of the organic electrolytes?
Now, electrolyte has to serve a lot of functions: viscosity, cost, conductivity, all those. So some electrolytes can provide, ionic liquid can provide some advantages like stability, electrochemical stability, windows and things like that. But at the end of the day, you should be able to charge and discharge at a particular reasonable rate. So if it cannot sustain the charge, meaning the ionic conductivity, the lithium ion transfer, then it will be handicapped. More importantly, cost is important. People say batteries have to be, the cost has to be cheap like dirt, like cheap like sand, right? So that's what it is. So the cost, if you can make an ionic liquid satisfying all the properties and lower the cost, that will be great. But you have to see, right now we are not using in the practical batteries.
Yes, sir. One question is the replacement of the polymer electrolytes is possible, or even solid electrolytes, whether it could be substituted in the, because organic liquids are inflammable, whether we can have solid electrolytes based on lithium-ion conductors is possible.
Yes, that is the ideal battery. If you can have a polymer electrolyte with adequate conductivity, then you do not have to use the liquid electrolyte. You can make all solid-state batteries. Unfortunately, we do not have a polymer with adequate lithium-ion conductivity. We don't. So what people try to do, we have ceramic oxides. They have high lithium-ion conductivity. So what is going on right now is mix the ceramic solid electrolyte with good ionic conductivity with a polymer to make a composite so that you get flexibility and try to use it. So that's what is happening. But how will be pore free, because it cannot be porous, right? Dendrite will go through. So all those issues you need to look into. So that is research, not commercial or anything yet, but a lot of research is happening. So battery looks simple, but it is a very complicated problem. It's not easy. What we use is the technology developed 30 years back, and we are still stuck with that. Nothing, lot of engineering has changed, but the basic chemistry has not changed. So it's very complicated. Too many things have to be satisfied. Unfortunately, I cannot do that in a 30-minute talk. Whatever I said, a lot of things, I do this in a course in the whole semester, starting in January, ending in beginning of May. So that's what many things I was saying here. I'm teaching in a class. So I was going faster, but there is a lot of things we need to understand.
Yes, sir. One final question from my side about the nanocrystalline oxides as cathodes, whether they have improved performance in the product level, or and I saw that some characteristics have enhanced in terms of charge transfers. So whether it's worth looking at it or it is academic interest.
So nanomaterials, if you have, they are smaller particle. So the lithium ion transfer from one particle to another particle will be easier, faster. But nanomaterial will bring two problems. One problem, for cell phone, laptop, and car, volumetric energy density is more important than gravimetric energy density. What does that mean? How much energy you can store in a given volume or size, as opposed to how much energy you can store in a given weight. If you have nanomaterial, they will not pack well. They will occupy more volume. So volumetric energy density will go down. So your battery, for the same amount of energy, same material, everything same, lithium cobalt oxide, you make nano instead of 5 micron or 10 micron particle, actually 10 micron particle, then your battery size instead of being this much, it's going to be that much. That's not good. So nobody is interested to use that for that battery. Second problem, you have solid electrode, you have liquid electrolyte. They will react with the surface of the cathode and anode. If you have nanomaterial, they will have high surface area, lot of electrolyte will have surface reaction, active working lithium ion will be trapped in that reaction product. That is called solid electrolyte interfacial layer. So you will have a lot of loss. So in a sense, nano is a bad word, or bad thing for lithium ion batteries. You have to use nano only when you are forced to use it. Lithium ion phosphate, bad electronic conductor, bad ionic conductor, you have to make it nano, but its operating voltage is 3.5. SCI, solid electrolyte interfacial layer formation, is not there, so it is okay. Silicon, same problem. Volume change, so you have to make it nano. But they have a lot of problems. Batteries based on lithium ion phosphate, very low volumetric energy density. That's why nobody wants to use it in the car, particularly in the US. For India, that is okay because you need only shorter distances. Auto rickshaw is a great technology. Lithium ion phosphate. So for India, the battery technology, there is near term and long term. Near term, some technologies can be used. Other countries, very developed countries like US, will not be interested in that kind of technology for automobile. But India, auto rickshaw or shorter distance people travel. So lithium ion phosphate may be okay. So
yes, sir. Thank you very much, sir, for giving your time. Now it's midnight. Thank you very much. Now I go to the convener and to the organizing secretary. Thank you.
Thank you very much. Have a good day.
Thank you, sir.
Thank you, sir.
Okay, thank you.
Now let us move on to the next
Thank you
talk.
very much, sir, for joining with us. Yeah, we are waiting to meet you. So I am extending my welcome to all the speakers over here. It is unfortunate that we are not able to meet you in person. So we are all welcoming you to visit VIT. And so many scientists from BIT and our professors from Department of Chemistry are very eager to meet you in person. So extending my warm welcome to you, sir. Thank you so much for joining with us. Thank you once again. Thank you.
Thank you very much.
Thank you
Thank
very
you.
Professor
Yeah,
Srikanth,
I welcome Dr. Srikanth Hariharan. Already is online.
Yeah, can you hear me? My
Yes,
voice.
sir. Yes, yes.
Okay, great. Yeah.
and to
So
the-
what?
Yes, over to Dr. Vijayaraghavan, sir. You can introduce the. Yeah.
Thank you, Professor Cheralathan and Professor Medicinal for the opportunity. And again, welcome to Srikanth, the second panel speaker of the first session. Professor Srikanth Hariharan is currently working as a professor in the physics department of University of South Florida, Tampa. And he had his graduation at before he moved on to the Tampa, and he is named associated with magnetism, phenomenon, and materials as well. And he has recently focused on to energy as well to biomedical applications of these magnetic materials. And he has got a lot of publications. He is the editorial board of many journals. Can you move the slide?
Can hear.
Hello,
Hello.
Professor, are we here?
Yeah, I'm here. It got disconnected.
Okay.
But Srikanth, can you hear me? Is the audio clear?
Now I can hear you. Yeah.
Thank you. So you have got publications over 265, citations about 7,500, its index about 49 with 2 years patents. Is given over 300 invited talks, colloquia and seminars, 260 contributory presentations. He has helped PBIT, our department, this department, by evaluating 2-3 theses when he was the dean. I could see that he evaluated 2-3 theses for us also. Thank you for that. He has graduated about 15 students have graduated from him. He has mentored about 12 postdoctoral researchers, and he is the editorial board of he is full-paid scholar. Also, he is in the IEEE Battery Society as a distinguished lecturer, Mary Curie Fellow, American Physical Society Fellow, Institute of Nanotechnology Fellow, Associate Editor of Applied Physics. So, distinguished professor from USA. And if you recall that he was one of those pioneers to set up STM in IISc way back in the 90s, I would say that he was the first person to make the chip, which is 1 atom thick chip to form the STM. So it is with immense pleasure that I invite Professor Srikanth Hariharan to deliver the plenary lecture. So 45 minutes for logistic purposes, we have made 30 plus 35 or something. Then question of the session time. Then also some time for the some buffer time for the connectivity. Please, Srikanth Hariharan.
Okay. Well, thank you very much. It's 1 o'clock in the morning, so if you feel that I'm all over the place, that's because of the time here. So let me go ahead and share my screen here. I hope all of you can hear me.
Yeah.
Okay, so here we go. All right, can you see the screen there?
Yeah. Okay.
And full screen too? Okay, all right, okay. Well, thank you very much for inviting me to this workshop, and thanks to the convener, Professor Mary Saral, thanks to Dr. Cheralathan, and my very good friend, Professor Vijayaraghavan, that I've known for many years now, more than 30 years almost. And it's a pleasure to be here. I've left India back in '94. I've been in the US for more than 25 years, but I do come to India many times, often, sometimes even twice a year. I've always meant to visit VIT. Professor Vijayaraghavan has invited me many times. I never had this opportunity, but it's great to connect with you guys here in this virtual conference. And I look forward to possibly whenever travel starts, maybe next year in 2021. I look forward to visiting your campus. Okay, so today I'm here to tell you a story. And I was thinking, well, this is Tamilnadu, Vellore. The best way to start is with a message. And I guess in Tamil Nadu, of course, movies are very popular. So I found this song. This is your Indian Dalapati Vijay in a song that says, "Let me tell a Kutti story." So that's my job today. What I'm going to do here this morning is to tell you a Kutti story. Kutti in Tamil is basically very tiny. Of course, by tiny, I mean nanomaterials, nanoparticles. But then the story that I'm going to talk about is not about the particles themselves, but what you can do to the particles. Can you do some surface modification, some surface engineering, and use that for enhancing the properties specifically for nanomedicine and cancer therapy? Well, theranostics is just a term that combines therapy and diagnostics together. Okay, so I'll tell you how magnetic nanoparticles can be useful for both therapy and diagnostics for cancer. So that's my task for today. But let me first tell you where I'm from. If you look at this is Florida right here, and it's a peninsula like India, right? It's got water on all three sides except for the top. And I'm in the city of Tampa, that's right there. Okay, so if you compare with India, this is like the Goa of India on the west coast of Florida. Okay, the beaches here are also very famous, very popular, like the Goa beaches that you have here. They're in India. In fact, the Gulf Coast beaches are considered some of the best in the United States. In addition to very popular beaches, we also have a number of universities, large universities in Florida. It's a highly densely populated state. And we are a pretty large university. We're the 12th biggest USF, University of South Florida. I would like to welcome you all. Basically, it's the 12th biggest in the country in terms of number of students. There are about 48,000 students. And it's not as big as UT Austin, where Professor Mandiram is. That's much bigger. It's, I think, the top 2 or 3rd, or even could be the largest school, largest university in the country. But we are up there in the top 15. But something unique about the physics department is that we offer a PhD in applied physics. And you can go to the website there, take a look at our programs. Material science is our strength in our department. And so we offer a PhD in applied physics, and it turns out that this is unique in the state of Florida. You may have heard of other universities, University of Florida, which is in Gainesville, Florida State University in Tallahassee, where the National Magnet Lab is. All the big magnets are there in Tallahassee. However, they don't offer a PhD in applied physics. So if you want to get a PhD, live near some of the best beaches in Florida and get a PhD in applied physics, we are the only choice. So please pass the word around. We would love to have more students from India, and especially from Vellore and Chennai and other places. I'm giving talks thanks to all these wonderful work done by all my students and postdocs over the years. Some of them are current students. Some of them are moved on to other positions, some postdocs. There are many areas that we work on. So these are some of the areas that my group focuses on. Today's talk is going to be on magnetic nanoparticles for specifically nanomedicine and for cancer therapy applications. Okay, so this is the outline of my talk. I'll start off by a basic introduction to magnetic anisotropy. As I said, anisotropy is the key to tune the magnetic properties in nanoparticles as well as many materials. And I'll show you that one can do that by surface modification and also by changing the shape of nanoparticles. We can tune the anisotropy and hence the magnetic response. The main part of the story is going to be how the anisotropic nanoparticles can be used for biomedical applications, and that too specifically for cancer therapy. I'm going to take this off. The third thing is, I'm not sure how many of you have heard of the, it's an American TV show, Dancing with the Stars, and it used to be quite popular here. Well, I'm going to talk about Dancing with the SARS. The SAR here, S-A-R, stands for specific absorption rate. It's a figure of merit that is used to evaluate how cancer cells can be treated or killed using heating or hypothermia. So this is what I'm going to try to see if we can improve it by using different kinds of materials and using anisotropy as a possible tool to change the properties of the nanoparticles. Okay, so what is magnetic anisotropy? Of course, you want to talk about magnetism, then I have to start with quantum mechanics because magnetism is rooted in quantum mechanics. Well, we can't do that, but I have to start somewhere. So let me start with the magnetization vector, okay? And that's your magnetization vector. This could be a ferromagnet, and that's the total magnetization. You apply an external field, and of course, the magnetization vector is going to feel the strength of this, and it's going to rotate. And you also have these ferromagnetic domains. So for the time being, let's ignore that. Let's just assume that this is just a single domain. And then you can see that this interaction can be represented by a simple equation here. Remember, I'm a physicist, so I have to show at least one equation. So this is my equation slide. It's a fairly simple equation. Basically, what it tells you is that the total energy is a competition between the external field, which is the Zeeman term, and the internal magnetic energy, which is this part here, and that's the anisotropy energy. Okay? So anisotropy is very important because it determines the shape of the magnetization curve. For example, whether you have a easy axis of magnetization or you have a hard axis of magnetization, whether you have a soft magnet or a hard magnet, it's all determined by the competition between the external field of the Zeeman energy and the internal energy, which is typically the crystalline structure and other aspects, shape, for example, that could lead to the effective magnetic anisotropy. Of course, you minimize this, and this is how we minimize it, right? And that's the equilibrium position that the magnetization vector will take, okay? Well, that's how you get all these shapes of different curves. And this is important because I'll tell you that by controlling the shape of magnetization and the approach to saturation, we hope to change the properties and improve the characteristics for cancer therapy. I'll get to that later on as we discuss that. Okay, so well, what about the structure? This is simple uniaxial anisotropy. There is no preferred direction here, which is typically the case for most spherical or symmetric nanoparticles. However, we can also handle higher order symmetries, cubic, for example, no problem there. We can take the different directions and do that. But when it comes to nanoparticles, there are many aspects that go into the anisotropy. For example, let's start from the left here. You see that the surface is in fact, nanoparticles are all about surfaces, right? Anybody that is working in nanomaterials of any kind, you're a surface scientist because what you're doing is basically the surface atoms are being controlled, and the surface atoms play the most important role in determining the physical properties of the material, whether it's magnetic or whether it's semiconducting, it's the surface that matters. So that's one way to change the anisotropy, by changing the surface structure or the way in which the atoms are arranged. Shape is quite obvious, because if you give a preferred shape, like for example, if you take a nano wire or a nanotube, the longitudinal axis is the preferred direction. So it's easy to magnetize it along the longitudinal axis. So in that sense, shape anisotropy is very obvious that you can actually change the anisotropy and the nature or the shape of the magnetization curve. Strain is important, especially if you have interfaces. When you have thin films, for example, you can have substrate strain that affects the magnetization of the magnetic film, and that can be used for determining, again, the preferred orientation and the way in which the magnetization curve approaches saturation. Configuration is something important. You can actually couple different kinds of magnetic particles or even non-magnetic metallic particles with, let's say, magnetic oxides, and you can form these clusters. And these clusters have a geometric configuration, and using that, you can also manipulate the magnetic characteristics. Last but not the least is what is called unidirectional or exchange anisotropy. You may have heard of the term exchange bias. It's a very important term in spintronics. Those of you that are familiar with the spintronics, as you know, this is spin-based electronics. So essentially, in this case, typically you take a ferromagnet and an antiferromagnet and you make a sandwich. Then the interface energy is governed by the interaction between the antiferromagnetic spins and the ferromagnetic spins at the interface, and that results in the so-called exchange coupling or exchange bias. It results in the shape change of the hysteresis loop and also a shift in the hysteresis loop. This is well known and very important for the spin valve, spintronics community. In fact, most of the elements such as the spin valves, MRAM devices, for example, they all work based on this exchange bias that is so important in spintronics. Well, today I'm going to tell you that it's not just spintronics. Turns out that exchange bias, or this exchange coupling between antiferromagnets and ferromagnets and using the interface, can be effectively used for biomedical applications such as cancer therapy. So that's something interesting, that something which is very useful for spintronics is also useful for nanomedicine applications. Okay, so it turns out that anisotropic nanoparticles are actually a lot easier to make. It's actually very hard to make a perfectly symmetric nanoparticle, okay? So it's a lot easier to make anisotropic nanoparticles, and not only that, anisotropic nanoparticles are omnipresent. They're around everywhere. And just to illustrate this, I'm going to show you 3 TEM images. That's what they are, transmission electron microscope images. And it's the same material, iron oxide, magnetite, Fe3O4, or the variations of iron oxide, different ferrites, spinel ferrites, okay? That's the only material here. Unfortunately, this talk is going to be focused only on magnetic oxide, namely iron oxide. There's a reason for it, because if you want to take magnetic nanoparticles and use it for biomedical applications for medicine, it has to be biocompatible. And it turns out that iron oxide is the only biocompatible magnetic material that's allowed by the FDA for treatment, okay? So we don't have too many choices. We cannot think about exotic perovskites or other kinds of materials for cancer therapy. We have to stick with biocompatible iron oxide, magnetite, and ferrites. Okay, so what makes this 3 TEM images interesting is the source where these nanoparticles come from. Let's start with the left. It turns out, and some of you might guess what it is, it turns out these are magnetite nanoparticles in bacteria. There are these bacteria which are magnetotactic bacteria. They actually produce nanocrystals of magnetite, and they chain them up using dipolar coupling. They chain them up and essentially form these short chains. And the reason they're doing it is exactly what the Chinese did when they discovered the compass. All right. Basically, they discovered what is called lodestone magnetite, and they found that can basically iron or magnetic materials can respond to it, and they used it for navigation. So these bacteria are essentially making tiny compasses, and they're making this to search for a source of food. That's what they're doing, right? The second example is out of this world, literally speaking, because what you're seeing there are the same magnetite nanoparticles, but these are magnetite particles that are found in chunks of meteorite from Mars that crashed into the Arizona desert, okay? So, well, don't try to put this and this together, because, magnetite particles in life forms, magnetite particles in rocks from Mars. So whether there's life on Mars, that's not what we're going after here. I just wanted to show you that basically you can find these anisotropic structures. For example, you can see these chains, which is anisotropic. You can also see these faceted structures. They all form naturally in various systems. Okay. Now it turns out that those of you that are interested in the history of nanomagnetism, it started about roughly in the 1930s. The first set of scientists that started working on nanomagnetism, nanoparticles, and also even defined the term superparamagnetism and other terms that are very well known in the field now. They are not chemists, they were not physicists, they were not engineers. Turns out that the first group of scientists that studied nanoscale magnetism are geologists or geophysicists. They were looking for magnetism in rocks. So here's an example of that. The third is actually, these are nanoparticles. You can see the similarity between these faceted nanoparticles and these are man-made faceted nanoparticles. They were produced in a plasma chamber using microwave plasma at Carnegie Mellon University, at a good friend's laboratory. His name is Professor Mike McHenry, and they can make large quantities of these ferrite nanoparticles in this plasma chamber. So I just wanted to show you that these are all anisotropic nanoparticles and they are there. So can we put them to good use? Can we put them to use for biomedical applications? Okay, so let's now start thinking about what kind of biomedical applications in which these magnetic nanoparticles can be applied. There are several that come to mind. I just picked a few of them to illustrate. If you start with the one on the left, let's start over here. I have a highlighter here. Let's see, that works. Okay, it does. There you go. So the first one here is targeted drug delivery. Now, because these magnetic nanoparticles, they're super paramagnetic, they respond to magnetic fields. And when you remove the field, of course, they go to a demagnetized state. That's why they're super paramagnetic. They're magnetized easily, but then when you remove the field, the magnetization goes to zero. Okay, so they don't have hysteresis. They don't store a remnant magnetization when you remove the field. That's the advantage of these super paramagnetic nanoparticles. Now imagine these super paramagnetic nanoparticles, you can functionalize the surface. These particles here, you can functionalize the surface, and then you can inject them into a living tissue, in this case, a mouse, for example, and non-invasively with an external magnetic field, you can guide these particles to the area of the tumor, for example, or any kind of a disease where you're taking the drug and deliver it locally. So this is targeted drug delivery or site-specific drug delivery. In comparison, what we do mostly is systemic drug delivery, right? When you take a drug, you're either taking a pill, swallowing it, or you're taking some kind of a tonic or whatever it is, right? And this is going through your entire circulatory system. Essentially, your entire body is going to have side effects. Instead of just treating the disease, you're exposing the entire body to the effects of this drug, okay? Now that should be avoided. So the future lies in this targeted drug delivery. And as I said, magnetic particles can act as navigational aids, in this case, as ships that carry the necessary drug molecules because they can be easily functionalized. And you can actually, using a magnetic field, take it to the local, to the area and then release the drugs there. So there's a lot of work going on in this field. We're not very active in this area, but we are active in this area here. It turns out that magnetic nanoparticles can be used for MRI enhancement. Okay, MRI is magnetic resonance imaging, which is very popular, used in many hospitals, and that's how you get the images of tissue. Brain, for example, is done by MRI imaging. It works based on the principle of nuclear magnetic resonance. Remember that we are talking about nuclear moments in this case. These are much smaller than the electronic moments. So they are really small. And essentially what you do is that the protons, the water protons, you can set them into precession, the nuclear spins, by hitting it with a DC field and a combination of a perpendicular high frequency radio frequency field. And then what you do is that you turn off the radio frequency field, these precessing spins, they start dephasing, right? And the time it takes, there are two time scales here. These are relaxation times, T1 and T2. From that, you get these images, which are the MRI images. Now, it turns out that because the nuclear moments are very small, is there any way we can enhance the local moment? Magnetic nanoparticles can be introduced. And then what they do is that because of the fringe fields of the magnetic particles themselves, because they're magnetic, they're super paramagnetic, the fringing fields will interact with the nuclear moments and the precession. So which means they completely change it. And essentially the difference in the time, because of the presence of magnetic particles, turns out that one can actually use it for increasing the contrast. This is a very mature field. A lot of work has been done. And in fact, MRI enhancement has been shown to be very effective using magnetic nanoparticles. More recently, this is pretty exciting. In this case, it's actually the nuclear moments, and also you're not imaging directly the particles, you're imaging still from the relaxation time. In this case, you can actually image directly the magnetic particles that are injected. So this is called magnetic particle imaging, okay? As opposed to magnetic resonance, this one is magnetic particle imaging. And this is actually came out a few years back from a group in Berkeley. It's very popular. You can see that the contrast is extremely high. For example, this is with magnetic particles, MRI, and this is with the MPI. You can see there's a big difference. You can see a lot of detail here. So again, this is the future of medical imaging, magnetic particle imaging is going to replace, hopefully, in most cases, MRI, so that you get a much better, higher contrast picture. I'm going to skip this. We can also do cell separation, but the rest of my talk is going to focus on the possibility of killing cancer cells using magnetic particles. And how do we do that? We do that with what is called hypothermia or magnetic heating. We allow the magnetic particles, we apply an external field which causes the magnetic particles to get excited and generate heat. I'm going to tell you how this happens, and I'll give you examples of how we can go ahead and do that. Okay, so, well, keep in mind that the magnetic particle is just one entity. When you want to think of a cancer therapy, for example, injecting something into the bloodstream or into a patient, for example, you need to work with a system that is hybrid, magnetic particles. There are various kinds of particles. This cartoon here is very interesting because all these things are important. The size is important. I'll mention that later. Surface chemistry is very important because these particles need to be biocompatible. You also need to attach various things. For example, if you want to target certain tumors, you need to have antibodies or aptamers, targeting ligand that is attached so that you are specifically binding to those tumors or cells that you really want to affect. Also, there are various types of particles, conjugates, and essentially what we are interested in, I'm going to focus on, is that can we change these particle shapes and sizes chemically? We can make these particles. I'll show you some examples. And will this have an effect on the overall efficiency of these particles for therapy? Okay. All right. So cancer, well, right now it's all COVID-19, but keep in mind that cancer has been around for a long time, and that is something that we need to somehow control and come up with new therapies, effective ways in which to treat cancer. Okay, so this is 2017. You can see that cancer pretty much affects the entire world population. These are the stats for India. You can actually see that there's a cancerindia.org.in. You can go and find the current statistics. I got it today, and it turns out roughly about 12 lakh people are affected by cancer every year. These are new patients, new cancer patients, and out of which approximately on average every year, there are close to about 7.8 lakh deaths. Okay, so cancer is a killer. Forget COVID-19, it's going to disappear hopefully with a vaccine, but cancer is something that should always be, we should look at therapies to try to eliminate it. And so we do need to come together. Okay, so one of the things that comes to mind is that, well, cancer treatment, that's the job of the medical doctor. It's not true anymore. You as a physicist or a chemist or an engineer, we all need to work together. And in fact, we can try to come up with various ways to understand the problem and also to effectively come up with new ways. And magnetic hypothermia is one of these new possible therapies that have been recently come into the forefront, which is developed using chemistry and physics and engineering principles. Okay. All right. So just to give you this idea, here's the Physics Today, which is a popular magazine for physicists. And this is the July 2019 issue. And you look at this article, it talks about mathematical modeling and physical and mathematical modeling, how that has really improved understanding of the process of metastasis. Metastasis is the process by which cancer cells grow, and they also move to different parts of the body. It's very important to understand the mechanism, the process to arrest this. And this gives you an idea how even modeling, mathematics is able to help understand the process. Okay, so now let's talk about magnetic hypothermia, or how do we generate heat with magnetic fields? Well, as I told you, we are going to apply AC magnetic fields, large amplitude, high frequency magnetic fields to magnetic nanoparticles, and that will generate heat. I'll explain to you how it does that, okay? But what happens to the cancer cell? If you want to destroy a cancer cell, you need to break the cell membrane or completely destroy it. So that's the idea. So in this case, the cell membrane is going to be destroyed by heat, okay? And I'm not a biochemist, but if you want to know the process, turns out that there's protein denaturation, the cell membrane restructures, and eventually the cell is dead, okay? We call this process
as driving the cell as apoptosis. And this happens, actually, you don't need to heat it up very much, just a few degrees Celsius above the human body temperature, okay? So the cancer therapy window is 40 to 45 degrees Celsius. So you need to be able to generate local heat of 40 to 45 degrees Celsius, and cancer cells die. They don't survive hot temperatures. They don't like Florida, for example. It was 36 degrees Celsius earlier today. So it's almost like Vellore here, the same. Okay, so we need to bring the cancer cells to Vellore temperature, summer temperatures, and that's how we kill them. And how do we do that? By this AC magnetic field or AC magnetic hypothermia. Now it turns out that there's one company that has commercialized this and is actually doing pretty well. They are doing a lot of testing. And this is a company that is based in Berlin. It's MagForce. And what they do is very simple. They inject it, and you can see that it's almost like an MRI machine, right? With the patient going into the magnet. So essentially, they take the particles to the tumor area, then turn on an AC magnetic field, and it locally heats the tumor, and it shrinks the tumor because the tumor cells are getting destroyed. So what is the physics behind this? The physics is very simple. We need to have a large hysteresis, okay? Now, those of you that are working on magnetic nanoparticles know that super paramagnetism means there is no hysteresis, right? You remove a field, it just comes back to zero because of the particle size being very small. The hysteresis we're talking about here is not the DC hysteresis, but it's the AC hysteresis. So the physics is very different. The process is very different. So you know that if you have a hysteresis curve like this, the area inside the hysteresis curve is dissipation, and dissipation here is in the form of heat. And that's how we generate local heat to kill to fry the nanoparticles, okay? So essentially, this is the AC hysteresis. And the way to understand this is that when you apply a high frequency, large magnetic amplitude signal, essentially the particle is saturating. And then if you, in the other cycle, it's saturating on the other side. And when it's fast enough, the large magnetic moment of these nanoparticles, think of each particle as a super spin. So it's unable to follow the high frequency, so it goes out of phase. And because of that, you have this hysteresis loop, and that's your hysteresis loop. We want to maximize it. We want to maximize the area. Every therapy or every kind of technique that you develop, you need a figure of merit that you need to improve. The figure of merit here is the specific absorption rate, or SAR. And simply put, it's just the area multiplied by the frequency of the AC field that you apply. Now, keep in mind that this is something that is going to be injected inside the human bloodstream, inside the human body. So you don't want to really put in a lot of particles. You need to keep the toxic level low. So we need to come up with strategies to improve the material science of these particles, as well as to come up with ways where we can actually use only few nanoparticles, small volume of nanoparticles, and still be able to increase the figure of merit, or the SAR. So that's the goal. I apologize, this is my second equation slide, only this, I promise, no more equations. But it's easy to understand from this that the power dissipated, that is the heat that is generated. It's proportional to some kind of a product of the AC field amplitude and the frequency. And as you can imagine, because of the fact that these are trying to, there's a relaxation process involved, there's a relaxation time. In fact, there are two relaxation times that go in there. One is the Brownian, the other one is the Néel relaxation time. For example, the whole particle itself can have mechanical motion, and that's your Brownian time scale. And of course, the magnetization vector alone can coherently rotate when you apply an external field, alternating field, and that is your Néel magnetization. So a combination is important, but it's the Néel term that is more important, because obviously particles can be arrested, right? In a cellular environment, which is fairly viscous, particles may not have mechanical motion, whereas Néel, or the magnetization rotation, is the more important one. Okay, so here are SLP is the same as SAR. This is specific loss power. It's the same as SAR. Some people use SLP. Okay, this one is important because it tells you that one of the simplest ways to increase the SAR, or the heating efficiency, is to make nanoparticles with large magnetic moments, or large magnetization. Well, that's easier said than done, because if you make nanoparticles, as soon as your particle size goes down, the magnetization drops like a rock. And this is because the surface is disordered. The surface spins are disordered, so the ordered magnetic phase volume goes down. And so essentially it's very difficult to make magnetic nanoparticles that have the same magnetization as the bulk moment, for example. Size is very important. It turns out that the best particles for hypothermia are not too small, not too large. The highest power dissipation is actually somewhere in between. There's a sweet spot. So it is not actually single domain particles, and it's not multi-domain. Okay, somewhere in between. It's the transition between single and multi-domain. And also for health considerations, it is very important to not keep the particles too small. For example, if you take particles that are 10 nanometers, 5 nanometers or lower, there's the higher chance of these particles penetrating the so-called blood-brain barrier. They end up going to the brain. This is the last place you want the particles to go when you want the particles to go to the tumor, right? Particles going to the brain is a major hazard, and that's one of the reasons why FDA approval has been very slow. FDA is an agency, the Food and Drug Administration. Every country, India, all countries have a regulatory agency for this kind of bio research, medical research. So they're very extremely slow in approving any new techniques because of these issues, which remain to some extent unanswered. Okay, now how do we measure the magnetic hyperthermia? All right. It turns out that we do two sets of experiments, one done in Florida in my lab at USF, and the second one we take the particles and send it to Spain to collaborators in Basque Country in Bilbao, and we measure the same SAR. This is the same figure of merit done using calorimetry. In this case, we have an AC power supply. The particles are in there inside an inductive coil, and then we apply an AC frequency, and we have a thermometer here, right? A temperature sensor, and we can actually measure the rate at which the temperature increases. Remember that you need to increase the temperature to about 40 to 45 degrees Celsius and hopefully stop there. You don't need to overheat, right? And if you don't apply the right conditions, you will never get to the temperature. So this is what we need to monitor here in the calorimetric method. Our data looks like that. As you can imagine, that's the hypothermia window, 40 to 45. We need to get there as soon as quickly as possible, right? So we can apply different amplitudes. And in this case, our system works only at a fixed frequency. It's 325 kilohertz. These numbers are important. We can only apply a few hundred kilohertz. Should not apply more than that. I'll tell you why. Okay, and these are the amplitudes. And you can see for these manganese ferrite nanoparticles of about 20 nanometers average size, we can see that the hypothermia treatment is effective for about 500 Oersted applied AC field at a frequency of 325 kilohertz. Okay. If you apply a large field, you will overshoot this window, overheat it, not needed. And of course, if you don't apply the right field, you'll never come to this hypothermia treatment window. Okay. The saturation is because of the equilibrium, the thermal equilibrium achieved between the particles and the surrounding medium, in this case, cells or any other environment surrounding that. That depends on the latent heat and the specific heat of these particles. Okay, so we take the particles and ship it to our collaborators in Spain, and what they do is they actually can measure the entire hysteresis loop. Okay, so they have this big, large AC magnet that they've developed to apply large magnetic fields, high power magnet, and essentially their data looks like this. And they can actually measure the complete hysteresis loop and get the area inside the loop. Okay, in that case, they get the SAR. So you see SAR on the same particles. We do it with two different experiments. For students and researchers, younger researchers in the audience, in the people that are logged in here, just keep this in mind. If you want to publish something in a high impact journal, Nature Materials or PRL or ACS, Nano, whatever it is, keep in mind that if you want to prove something, ideally you would like to prove that effect using two different experiments that converge to the same result, because you will have a more compelling case. That's exactly what we're doing here. We have one experiment done using the calorimetric method and the other one using the magnetometry. And here it's not just two different experiments, it's two different labs and in two different countries. Okay, my point here is that international collaboration in material science is very important. And this is why you need to look for your Fulbright Nehru fellowships or whatever it is and keep applying, because you need to get that experience, that exchange of ideas. This happens through international collaboration. Now, Can I take about 10 more minutes? Can someone answer me?
Yeah.
Okay,
Yeah,
yeah.
please go ahead. Yeah, you can. Yeah, please.
Right. Okay. Yeah. So why do I keep saying that? Why don't we just increase the magnetic field to Tesla fields, right? That can be easily produced. And also, why can't we just go to megahertz, frequencies, gigahertz frequencies? The answer is, this is a treatment for patients, human patients. Okay. You cannot exceed certain numbers, certain values, because high frequency, high field is dangerous. It's dangerous for the nerves. You can actually cause nerve stimulation. You can actually lead to stroke. So one has to be extremely careful in applying the conditions within limits of, as far as the frequency and the magnitude, the AC amplitude is concerned. In fact, there is a limit that is known as the Atkinson-Brezovich limit in the literature. It's a product of the AC amplitude and the frequency in those, weird SI units. It's that, but don't worry about the number. Think of it as a pain threshold. Suppose a patient goes to an ER, emergency room, happens in the US, is probably the same in India too. The first person that meets the patient, we call them a triage nurse here. And the triage nurse, he or she, the first question they ask the patient is, on a scale of 1 to 10, what is your pain level? And of course, you can say 2 or 3, or if you're really close to dying, you can say 8. So that is the pain threshold. And so this is what we need to keep in mind, that patients, because this treatment has to be sustained for about 45 minutes to 1 hour, okay, this hypothermia, for it to be effective. So we need to make sure that the patient can withstand the conditions for that amount of time. And different people, of course, have different pain thresholds, okay? Some of them are can actually handle more pain than the others. So this is not a fixed number, but it is a guideline for you to keep in mind that you cannot exceed some extreme values when it comes to these conditions. So we are very limited in terms of choice of the parameters that we can use to increase the SAR. Okay, so now I talked about all these things. What else can we do to improve the SAR? The materials, the nanoparticles, can we improve them? Can we make them better? Can we make them having large saturation magnetization? Well, here's the plot here. This is the SAR in watts per gram. That's the power per gram. And this is the saturation magnetization. And you see that, unfortunately, magnetic oxide, in this case, it's maghemite and magnetite, both are used, okay? It is very low compared to metallic iron, and iron cobalt alloy is, very, very high. But unfortunately, we cannot use them because they are not biocompatible. They're toxic. You might wonder, why can't I put iron? We take a lot of iron supplements. There are different valences of iron. Iron 2+ is very, very harmful. Okay, it can catalyze, it can become free radicals. So it really causes harm. So really, these are not allowed by the FDA, and only the magnetic oxide. We have to stick with this. So our hands are tied by the FDA because the choice is very limited as far as clinical trials, okay? When it comes to clinical trials, you want to make sure that it's completely biocompatible and non-toxic. Okay, so size I've already talked about, but anisotropy is a big question. And this is where in our group, we stepped in because we thought that we understood anisotropy in magnetism a lot. And we wanted to see how anisotropy has an influence on the magnetic particles. So we started some of the first experiments in this field of hypothermia by trying to correlate the effect of anisotropy in nanostructures with the SAR itself. Can we improve the figure of merit? Okay, but first, let's talk about this one right here. Can we increase the SAR somehow making a particle with larger saturation magnetization? We can do that if we do a hybrid particle, right? For example, we can go to core shell particles. And by core shell particles, I mean, if you take iron core, right? Iron has a large magnetization. And of course, the shell, if the iron is completely encapsulated by oxide shell, then it's biocompatible, right? Because the cancer cell will see only the iron oxide of the body. Humans will only see the iron oxide, and it will assume that it's biocompatible. But inside, you can have iron, which is completely encapsulated. So using a core shell method, it is possible to get higher saturation magnetization than just these solid spherical or solid iron oxide nanoparticles. So this is the first attempt we did. We got beautiful core shell particles. This is a TM image of iron core, iron oxide nanoparticles. However, it turns out, so we can actually do this. We can increase the saturation magnetization. So those of you that are, I know that many of you are interested in the chemistry. So everything that we do here, all the nanoparticles are done by simple solution synthesis, thermal decomposition, solvothermal techniques. And essentially we do that in the lab using iron pentacarbonyl. These are some heat treatments. So the most important aspects is it's more like an art. Some postdocs, some students are really good at it, and they can actually experiment and come up with their own recipes of making high quality magnetic nanoparticles. Okay. The main thing here is the reaction time, the reaction temperature, and also, the surfactants that you use to arrest the growth. And that controls the particle size as well as the shape. Okay. So this is what we do. So when we tried these core shell particles, there's a problem that we ran into. And it turns out that this is something that is known by the metallurgy community. It's called the Kuykendall effect. By the way, the term metallurgy has disappeared almost everywhere in the world. It's all become material science now. And I think Vijayaraghavan and I, we remember, in ISC, there was a Department of Metallurgy. I'm not sure if it's still there or if they changed their name, but basically it's all material science now, mostly that you see. But the early metallurgists, they actually faced this problem, because if you take a metal particle and insulating oxide, and it turns out that because of the differential diffusion of the metal ion in comparison with the oxygen ion, there is an instability at the interface. And because of the instability, you see voids, holes opening up. And these voids get bigger and bigger. And ultimately what happens is that the metal inside oxidizes, the shell becomes thicker. So you end up with a hollow nanoparticle. And this happens as a function of time. You don't have any control over it. This is Kuykendall effect. So you start by making beautiful core shell particles. You end up after some time as beautiful hollow nanoparticles. So if your goal is to make nice hollow nanoparticles, this is the way to go. Okay. And this was first shown by Paul Alivisatos and his group at Berkeley. And it's well known that if you want to make hollow nanoparticles, you can use this differential diffusion or the Kuykendall effect. So what we did was we did a time analysis. Obviously, this is not good for hypothermia because we want stable particles, right? We don't want the particles degrading over time, magnetization going down, SAR going down in an unpredictable manner over time. So it's not good for that, but it was a nice study where we were able to understand how it worked. So let me show you the SAR here. I'm going to show the SAR as histograms for easy comparison, okay? So if you look at the particle size, for example, it's clear that the original goal was achieved. For example, we wanted to get a higher SAR compared to the solid oxide particles. You can see that the core shell particles definitely is much better. As you would imagine, the iron is, has a larger magnetization, so it's much better. However, look at this graph here as a function of time. In this case, this is for one batch, and the time scale varies, so it's not very predictable. And you can see that as a function of time, the SAR goes down, and eventually when it becomes hollow, it doesn't heat up at all. So it's not useful for nanoparticles. However, we were excited because we thought that the hybrid, having a core and a shell and having two magnetic materials with an interface, that's the best way to go. Except that we should avoid Kuykendall effect, and we should try to look for all oxide core shell hybrid particles where there is this problem of metal ions and oxygen ions diffusing at different rates does not happen. So while we were doing this we were scooped in some sense. There was a paper by this Korean group. They actually showed that cobalt ferrite, manganese ferrite, okay, all oxide, no Kuykendall effect, stable core shell particles. They found that this is an exchange bias. Remember I told you about antiferromagnet, ferromagnet having an exchange bias because of the interface. So these are all tiny exchange coupled spintronic nanowires, okay? And essentially they also showed a high SAR, indicating that indeed the exchange or interface and isotropy is important for this application. All right, so we tried this. However, keep in mind that these are, I just took a look at this. I'm sorry, I went the other way. I took a look at this shell here, cobalt ferrite. Cobalt is poison. FDA is giving us a hard time even approving magnetic oxide, magnetite, okay, which is biocompatible. It has not given permission for clinical trials here in the US. Only recently it is doing it, okay? So cobalt is, forget it. You're never going to get permission for actually translating it into medical nanomedicine applications. So what my postdoc did was she made FeO, which is a Wüstite phase. It's a lesser known phase of iron oxide. It's the Wüstite phase. It's antiferromagnetic. So she made FeO core and Fe3O4 shell. Fe3O4 shell is biocompatible, so no problem. And it's all oxide, no Kuykendall effect. And we really got some nice results. She was very good. Her name was Hafsa Khurshid. She's now an assistant professor actually at in UAE in Sharjah. And she was amazing when it comes to playing with these conditions in making beautiful core shell particles. She came to me and said, but Srikanth, aren't we supposed to play with the shapes? I said, yeah, well, it's already difficult to make these core shell particles. I don't know how you would play with the shape, but go ahead. She went ahead. I'm glad that I said, do it. She came back with this set of samples. She actually was able to controllably change the particle from roughly spherically symmetric to cubic to these exotic star-shaped. And again, if you see, the anisotropy is increasing. In this case, we're talking about surface anisotropy. Surface anisotropy of these nanoparticles going up. So we can immediately check what the effect of SAR is. And this is perhaps the most important slide of this presentation. We were one of the first groups to show that as you increase the anisotropy, as you go from spheres to a lower symmetry system like cubes and higher anisotropy system like octopods, you see that the SAR goes up for the same biocompatible system. We don't need to go to different materials. We don't need to go to different oxides. For the same system, we can increase the SAR by playing around with the shapes, and in this case, the surfaces. So this is the message that I wanted to give you, that even with a basic system, like a well-known system, like a magnetite, Fe3O4 iron oxide, you can still do a lot of interesting possibilities by doing surface modification, by doing careful chemistry, and making sure that you're able to controllably change these particles. Let me go to towards the closure now, because I'm going to skip a few slides. I know that I'm running late. So let me just go to, we can also make these nano rods, and we do that by the so-called hydrothermal technique, like a pressure cooker. It's a pressure cell. In addition to temperature, time, and the surfactants, we introduce pressure also as a variable here, which controls the, the growth of the particle. So you can make these beautiful nano rods. And these were done by Raja Das, another postdoc. An interesting story is that Hafsa Khurshid, the other postdoc that made the core shell, she's originally from Pakistan. Raja Das, of course, from India, and had at a time when these two were actually competing in some sense, in a very friendly manner, of course. So for me, it was like watching an India-Pakistan cricket match. I had a great time because they were both extremely good, very good postdocs that were able to make these beautiful, high-quality nanoparticles. So again, in this case, we showed that increasing the shape really gave us some of the largest SARs. So these iron oxide nanorods that Raja made, to date, I think they are considered one of the best in terms of giving you the largest SAR. And we're trying to contact the company, the German company that I said, they're not willing to interact. It turns out that we can actually do better than what they're doing with the commercially available nanoparticles by going to these nanorods. You have to make very high quality particles, okay? So let me just go to the final slides here. Just one thing I want to point out is that everything that I told you until now is only half the story. No, I'm not going to take another 40 minutes. Basically, all these particles that you make, you have to test the biocompatibility, and that's the only way you can take it to the next stage of usually having them interact with cells. Okay, so we do that. In this case, macrophages. Macrophages love to eat anything. Okay, they're like phantom cells for us, easily available. And so we feed the macrophages, and these are nano rods into macrophages. We can actually put a dye so we know where they're going, and then we apply the alternating fields, and we can show that indeed hypothermia works. Okay, this is and I was giving a talk in France. There was a young lady who was actually working in this area, and she took a fast frame video. So what you're seeing here is the cells interacting with the magnetic particles, and they're actually fighting with each other. These are glioblastoma cells, glioma cells, cancer cells, and they want to really eat these particles. So yes, indeed, cancer cells love eating these particles. Let's feed them and let's kill them. That's the idea behind hypothermia. So basically, I'm going to also point out that in addition to heating, You can also destroy the cell membrane. That is the goal. Remember that you need to destroy the cell membrane. And there are groups that are working on magnetomechanical destruction. So in this case, they make these small particles, high aspect ratio particles, and then applying frequency, not high frequency, but low frequency fields, they can actually cause it to rotate and rupture the membranes. Okay, so let me say that hopefully I've convinced you that magnetic nanoparticles are very interesting and very important for nanomedicine applications, for cancer therapy. Very soon, once the FDA approvals and more clinical trials are done, we expect these to get to the hospitals probably within the next 5 to 10 year time frame. You would see this as a mainstream supplemental method for curing cancer, for killing cancer cells in the hospitals. So we're pretty happy about that. So there's some Tamil for you. Uruvalavu, size is very important. Size does matter, as Godzilla movie says. But we are talking about nano size. But nano has been around for a long time. It's not just nano size. It's the shapes, surfaces, and interfaces. Vadivam, merparappu, idaimugam. These are the three things that you need to play with in a lab to be able to extract your new physical properties, in this case, new magnetic properties. So with that, let me conclude by saying that was my Kutti story. So FML, Functional Materials Lab at USF, thanks you for your attention. And again, thank you very much. This is a very stressful time for all of us around the world. So stay safe and healthy. Thank you.
Thank you, Professor Srikanth, for the excellent illustration of physics, nanoparticle engineering, and then biomedical to cancer related to society applications. And I know that we are from Madurai and you put Sankam Tamil, I could see. Thank you for that too. And also at this time at 1 a.m. in the morning, and tomorrow you have to work at university, you may have to go on online teaching. Thank you for that. We'll have just two, three questions, just because others can ask by mail. I have just 2, 3 questions on the audience. One is the distribution of the size of the particles, whether that has relevance. You showed the shape, and I think you showed the size also. So someone wanted to know the size of the particles, what efficacy of the cancer cells destroy the function.
Yeah, this is an excellent question, because distribution in size is unavoidable if you make large quantity of particles. And it also depends on the synthetic methods. If you are doing chemical synthesis, for example, reverse micelle, for example, gives you a very good monodisperse particles. You can make them, you can control the size very, very well with a very small size distribution. But most other techniques, they give you a large size distribution. However, in general, the efficacy is the particle system. How does it respond to the AC field? So in some sense, the size itself being absolutely, monodisperse is not that important as far as the application goes. What is important is you need to make the particles which are highly crystalline, and that is the challenge. People can make nanoparticles, but you have to do that extra bit, the chemistry carefully, to make it highly single crystalline, because that gives you the largest magnetization possible.
Okay, thank you. One final question is on the polymer functionalization of the nanoparticle. Will it enhance the biocompatibility or getting absorbed into the system? They were asking about the polymer functionalization of the nanoparticle.
Polymer?
Functionalization of the nanoparticle.
Yeah. Polymer functionalization is absolutely important. In fact, it is most of the particles that I showed you, they've been functionalized either using PEG. PEG is polyethylene glycol. Okay. Now, polyethylene glycol is very well known. It's highly biocompatible. In fact, guess what? Those of you wearing contact lenses, you put it in your eye, right? It's pretty biocompatible. You're putting it in your eye. It's made out of polyethylene glycol. So it's called pegylation. Pegylation is normally done. There are also biopolymers that can be used. That can be ligands, aptamers. Antibodies have been successfully, bonded to these nanoparticles. So that's why magnetic iron oxide is very good for functionalization. For metals, gold, for example, is very important. Gold can be easily functionalized using thiol chemistry. So essentially, combination of gold and magnetite has been the best system so far for biocompatible applications.
Okay, thank you. There are a few other questions which I already mentioned, frequency and all that you have mentioned in the lecture. So my questions in the weekend, and let me again thank you for your interest part of this conference here. And we have two speakers from the USA, one on energy and environment, other on the healthcare. So the title is covered in the first session. I thank both the speakers for their keeping up the time, and we are mostly on dot with time. I thank you both the speakers, particularly now Professor Srikanth, for waking up to 1 a.m. in the morning. Thank you very much.
Well, it's actually 2 now because I'm one hour ahead of, 1 hour ahead of Mandiram. All right.
Yeah, thank you. I'll go over to the convener and the organized chief secretary.
Yes, sir. I join with Professor Vijayaraghavan in thanking you. Thank you so much for accepting our invitation. Looking forward to meet you in the campus, as I had mentioned already. And the Department of Chemistry is waiting to interact with you in person when you visit us. Yeah, thank you. And now over to Cheralathan, sir. I think we will have a short break. In another 5 minutes, we will be joining back.
Thank you, Professor Srikanth. We are excited to see some of the Tamil captions particularly. And also your lecture was very interesting. Thank you so much for joining us.
Thank you very much. Thank you for the opportunity.
Thank you. Thank you.
As ma'am said, we will join back after a few minutes.
Okay. So
Thank you, Srikanth. I'll get back to you in the weekend.
Definitely, yeah. Talk to you later.
Bye-bye.
Okay.
Yeah.
Bye-bye.
Bye-bye. Bye.
Professor?
Yes,
You can hear me, Professor. Okay.
yes.
So I will start the introduction in 1 or 2 minutes. Nice to see you, Professor.
Okay. How about you? So
Fine,
I
Professor.
heard that there's a really big problem in India right now.
I thought India will overcome this very easily, but it's getting a little difficult, actually. I didn't expect this. So Korea did really well.
It's okay. Yes, it's
Really well.
about there's a come and go a little bit,
Yes.
but not that serious. But you have to under control. Everything's under control.
But here it's not under control. We cannot, though the government is making a lot of steps, but the people's cooperation is not much there. So it is not reaching the peak. It's actually going and increasing at its own rate. So, and also we are under lockdown, our university is under lockdown. Even international flights are also not starting yet. That's the reason, like our postdoc student is unable to even go to Chennai. Even for going to Chennai to get the visa, it's not easy. He can't travel. He need to get an e-pass, even for traveling outside his zone to another zone. So this is a very difficult situation for us.
Yeah.
Even regarding
I
our
don't know. I
project
can
also.
really visit once again in this winter time.
They will postpone. They will postpone. They will postpone, Professor. Yes, they will postpone for 1 more year. So depending on the conditions, like we can arrange our schedule also.
Okay.
So, ma'am, Dean, ma'am,
Everything's going to be settled down at that time.
yes, Professor.
Yes, sir. I'm available. Yes, I'm ready.
Can we start? Okay.
Hello, Mari.
Sure. Yes.
How are you?
Hello, sir. How are you? Yes, we are
I'm
not
fine.
able to see your video. Yeah.
Uh-huh.
How is the situation there? I was listening to the conversation. Hope you're safe and your family is safe, your country is safe. So, are you working in your office?
Yes, I am working
Are you
on
normal?
the
So you're
office.
in normal
Yes,
situation
everybody
there?
working right now
Okay.
in Korea. There's no problem at all. So
And no
that,
online classes, no on is offline classes, no?
well, that class is last week is ended, and including the exam,
It's a
and
vacation time.
but the PhD student or graduate student always come to work, so it's no problem at all.
Because I remember when you left India the last day, so
Mhm.
we bought a lot of disinfectant and
That's right.
sanitizer.
That's right. I'm still happy.
So it is still, it is useful there actually. The
Well,
product is good.
at least it is useful at the very beginning that, the dental mask is so good for me.
Was
So
more
after
useful.
that, now it's everything is okay.
Okay.
So we can buy as we wish.
Okay. So Professor Kailas, Dean's ma'am's consent, so we can start. So I'll start with introduction. Ma'am, shall we start?
Yes,
Yeah,
yes,
sure.
sir.
Okay.
I welcome back all of you for this second session. We have two lectures in this session, and I request Professor Anand Prabu and Dr. Samiranjan Meher to moderate this session.
Okay, thank you.
Thank you, Dr. Cheralathan. So let me introduce the session speakers. So we have Professor Hong Du Kim from Kyung University, Republic of Korea, followed by Dr. Palani Balaya from NUS Singapore. So let me give a brief introduction about Professor Hong Du Kim. Dr. Hong Du Kim currently working as professor in Department of Advanced Materials Engineering for Information Electronics, College of Engineering, Kyung University, Republic of Korea. He completed his PhD in physical chemistry in the year 1987 from University of Wisconsin-Madison, USA, and followed by working as guest scientist in Polymer Division, National Institute of Standards and Technology, NIST, USA, and then as senior researcher in Polymer Science Engineering Division, KIST, Korea Institute of Science and Technology, Korea. And then he joined in KHU from 1991 onwards as a senior professor in KHU. Coming to his funding, almost he has ongoing and completed projects around $1 million US. I'll just read out one completed project. And the title of the project is more related to our conference focus also. So I will just read out. Development of non-grid type, large area pressure sensing system based on multi-frequency electrical impedance tomography via development of nanowave-based piezoelectric piezocapacitive hybrid fabric sensor. So far as my interaction with professor is concerned, this is a novel sensor where it's a hybrid sensor. The same material can act both as piezoelectric as well as piezocapacitive, and you'll be learning a lot of information in this professor's talk. Regarding his ongoing projects, I'm very happy to say that Professor Hong Du Kim is also the foreign PI in the India-Korea International Project supported by MHRD Spark. The title is Design Development of Eco-Friendly Piezoelectric Energy Harvester based on biodegradable polylactic acid. So when you talk about piezoelectric energy harvester, previously PVDF materials were very popular, but in Korea, they moved to the biodegradable polylactic acid. So this conference is going to focus on it, in the project. So professor is also adjunct faculty in VAT, so he last visited in January. And so his ongoing another project is also very interesting. It is more towards product development, and the title is Development of Smart Seat. For example, in the car, you are sitting there, development of smart seat, skin materials based on electronic fabrics. His publications are around 64 and 15 patents. So this is the introduction about Professor Hong Du Kim. Professor, can you start the talk now? So I'll pause to you.
Okay.
So you can share the slide, please.
Let me see. Okay.
Yes, I can see.
Let me see. I have to adjust it.
Yes, was your time.
Just a moment.
So initially the slide was visible. So Professor is using two different screens, I guess. First screen visible இருந்தது. இப்போ வந்துட்டு அவர் ரெண்டு ஸ்க்ரீன் யூஸ் பண்றாரு ப்ரொவிஷன். போயிட்டு வந்துரு.
Somehow the monitor system makes some problems.
Yes, was the dual monitor will have some issues for it. When the slide appears, I will tell you. I will also notify you, Professor. Now it's not visible.
Let me see that. I can go to the.
This is started, Professor. Started. It is there. We can go to the full screen.
Okay.
Yeah, no, it's fine, Professor.
All right. So everything goes okay.
Yes, Professor. Thank you. Please start.
Okay. Thank you for the nice introductions, Professor Anand. So it is about 4 months past since I visited the BIT, and I'm also that expressed that by sincere thanks to the all organizers. So today's talk is in a sense that the previous presentation that when I visited BIT, but I want to focus on some other aspect a little more. And today I'm going to talk about some hybrid piezo-capacitive piezoelectric pressure sensor for the 2D applications. And my content is just some sense market forecasts and some comparison chart of the various sensors and some of previous results regarding the piezo-capacitive sensor and the piezoelectric sensors. From this result, we want to make some hybrid sensor which can afford that piezo-capacitive and piezoelectric signals. So those kind of area I'm working on, and I'm going to talk about the detailing. And as you see that global market is, especially for the sensor area, that is globally something like 240 billion in global. And specifically that Asia Pacific area is remain the leader. It is because that mainly the China and Korea and India has a lot of the sensor product, such as some cellular phones and in a sense related. If you look at that area, that especially that IoT is one of the good example. And another thing is that the sensor, in a sense, incorporated into some consumer electronic product as well as a smartphone and the automotive. And to have this kind of 7 drivers, and especially I'm working on some wearable sensor material, especially. And it is because that the healthcare is one of the fast growing sector in a sense. It's about 13% per year. So that's why I'm working on this area. If you look at that conventional healthcare sensor, that something like ECG use some gel electrode, and in the case of the respirations, and it requires some CO2 gas analyzer. And in the case of the hot pulse wave, you can use some diode, especially that diode use, and some physical activity uses 3-axis accelerometer, as well as some gas analyzer. That this is a conventional way which is used in the medical centers. But nowadays, this kind of sensor, in a sense that incorporated with some kind of module, which is some small and flexible and lightweight module, such as some Bluetooth and Zigbee and those kind of things. So one of the examples here is that heads of skin make some athletic outfit so that they can monitor heart rate as well as activity and those things. In order to fulfill this kind of sensor area, the sensor must be somehow that that flexible, and in that sense, that the fiber or polymer film is the best. So in this regard, I'm working on some various pressure sensor area. I'm going to talk about some piezocapacitive as well as piezoelectric today. That, as you know, the piezocapacitive means that if you press a certain material, that capacitance or dielectric constant change, so that we can monitor the pressure. And in the case of piezoelectric, that if you apply some stress or strain, the overall polarization in the material change, so that you can monitor some pressure. That there is some good thing or bad thing of these two materials. In the case of piezocapacitive, it has a very excellent sensitivity and a good spatial resolution. So bad thing is it has some inherent that stray capacitance. So this is a bad thing. In the case of piezoelectric, it is responding very quickly, so that it's less than 0.1 hertz, or I mean the 10 hertz response time. Also, bad thing about this piezoelectric material, it's only sensing the dynamics pressure. That means that if you press it some certain thing, then you can pick up the signal. But if you just press it constant way, it doesn't pick up any signal. So that in many sense, we require this piezocapacitive type as well as the piezoelectric type of the sensing materials required. So that's why I'm just presenting today's talks. So if you look at some sensor signal, if you apply some external pressure, that in the case of piezoelectric sensor, it's responding very quickly. And as you see here, dynamic pressure, that it pick up the certain very details of that external pressure. But if you just press it down, and if you apply just a constant pressure, it does not pick up any signal. However, in the case of piezocapacitive sensor, that instead of differently, it's a dynamic pressure somehow slower than piezoelectric sensor. It's because of the piezo capacitive effect. It takes some time to monitor that change. But it is very good to monitor the constant pressure, so that in this sense that the piezocapacitive materials is good for some two-dimensional pressure distributions. So in that sense, I tried to use both material and simultaneously. That's what I'm talking about. So instead of just a regular film, for my experiment, I'm using some nanofiber web using this electro spinning process. And how to make this nanofiber web is just simply dissolve the polymers in some good solvent, and then apply the high voltage on the needle, and the collector side is just grounded. Then if you apply about a kilovolt or more, sometimes it's a 10 or 20 kilovolt per certain case. It depends on geometry. And you can see that here, that some telecom, and because the electrostatic charge is accumulated in this drop, so that one way is that the solution is, that the dragging to the ground line, and then, and a certain time later, the fiber, in a sense, expel each other so that you can have a very fine fibers. So that this left-hand corner shows that one of the example of the nanofiber web. So in this case, as you see here, there is a lot of void. And if you choose a proper polymer material, you can change the dielectric constant as you press it. So that's why we try to use a nano web instead of films, so that it sensitivity increases very dramatically. So for the piezo capacitive sensor, just we attach some electrodes on top and down, top and bottom, and then we can measure the capacitance. And during the measurement, we applied external pressure at the constant rate for the calibration, and something like 100 Newton per, 2 Newton per second, something like that. Also that we can measure the creep behavior and the relaxation behavior as well. So this is one of the example that, as you know, that this SBS is one of the well-known polymer, which is very elastic, but in our purpose, it's not as good. So as you see here, that if I applied about this red line means about 100 Newton difference, so that the distance between the electrode change, so that capacitance is going to be changed, as you see here. But as you see here, that using the SBS as material, the capacitance change only about 5 picofarad. It's very tiny. Also, this is a, that the behavior is not as good. So this each peak, that means one cycle of that, we apply that force from the 0 Newton to 100 Newton, and the 20 cycle we accumulate. And then we cross-link the SBS, then the behavior is going to be much better than the spun nano F, but still the capacitance change is only about 30 picofarad. It's not good for the real application. So we search for some different type of the polymer, in a sense, elastic polymer, such as silicon is another example. And it turns out that the silicon also is not good. And later that we find out that we have a higher dielectric material such as polyurethane. And then we finally choose some thermoplastic polyurethane was chosen because it has a dipole moment, the carbon nitrogen dipole moment, so that the dielectric constant is relatively high. So as you see here, that compared with the SBS, TPU give us much more the capacitance change. As you see here, something like more than 50 picofarad. Okay. Of course, that if we cross-link by chemical method, then the performance is better. Okay, that compared with this. Oops. Compare with this and bottom case. And then we search for the very different type of the TPU a lot. And finally, we find the best TPU system we called KHS system. And as you see here, compared with the middle figure, the middle TPU has small creep behavior. That's each time if I press it and release, and the value slowly increase. that means that it doesn't recover back to the original distance. But in the case of KHS, as the capacitance value at the press state, at least the press state, it gives us very constant value. That means it's very elastic. Although it takes more time to release it, when we release it, that the capacitor value must be go back to the original location, but it takes more time, so that it has a slightly clip behavior, but it's not that serious. And then we try to improve the sensitivity of this material. We included some of very tiny amount of ionic liquid, which is very high dielectric constant material. So if I include that, as you see, compared with this upper KHS versus KHS with ionic liquid, the difference in the capacitance is dramatically increased. Okay, so that finally we find out that one of the best system in this case. So if you take a look at one of the cycle out of the 20 total cycle, we can compare with the hysteresis of various type of the nano-based sensors. As you see that the SPS looks so good, but it's, as I told you before, the sensitivity is not good enough. In the case of TPO, if we cross-link, then from the 14% of hysteresis to go down to about 11% or 10%. As you know that the normal polymer system, even though it is a very elastic material, normally that about 10% of hysteresis is very normal. But we try to overcome this kind of behavior. And as I told you before, that KHS is a very good material. And then with a small amount added ionic liquid system, the capacitance change is almost 400 picofarad. Also, the hysteresis goes below 2%. It is a world best material in terms of hysteresis wise. Okay, so at least we know we have very good piezocapacitive material, KHS, with a small amount of ionic liquid. In some cases, we don't need this ionic liquid. And then let's move on to a piezoelectric material. You know that a good example is the PVDF, polyphenylene fluoride. Another example is the biopolymer. So polylactic acid is one of the well-known piezoelectric polymers. And these two materials has some different characteristics. As you know, the PVDF, without any process, it cannot be piezoelectric polymer system. It's if we stretch the PVDF, in the case of a film, even though we stretch it, it doesn't give us a piezoelectric signal. It's because the domain of a crystal is, in a sense, randomized, so that the total polarization is always zero. In order to become piezoelectric polymer, it requires some either direct polling or coronal polling is required. In the case of polylactic acid, it's not like a PVDF. It has some cyclic conformation, helical conformation. It's normally alpha crystal is a 10-3 helical conformation. But in this case, it's even though we apply some external force, it doesn't give us that dipole moment change. But once we draw it, it becomes beta crystal. It's called the 3-1 helical conformation. In that case, if we press it, that it gives us some shear piezoelectricity. But instead of using the film, we can, as I told you, that we can use some nanofiber web, either this PVDF or polylactic acid dissolved into solution and then electrospin it. Then at the collector area, that it has some high electric field exists, so that during the process of electrospinning, the dipole moment is aligned vertical to the collector area, so that in a sense, once you have some nanoweb material, it becomes piezoelectric material without any extra pulling, because during the electro spinning process, it gives us some aligned dipole moment we have. So from the out of this kind of two different kind of material, one is that polyurethane, which give us some piezocapacitance signal. The other one is a PVDF, which give us some piezoelectric signal, so that we can sandwich it. Then we can have two hybrid type sensor we can make it. So that from this material, we can make some hybrid INSO sensor quite time ago. As you see here, that we made three different for one INSO, so that as you see that the piezocapacitance, that we can see there's some difference between the 3 to 1, and as you see here that this working, the person has a very good working behavior. But it's also that the piezoelectricity, that is the signal behavior is much quicker, and also that similar result we can have it. And of course, we can run, and the signal become faster and faster, as you see here. So this is one of the examples. Okay. So that we can monitor that working behavior out of this kind of hybrid INSO system. Okay. Now, as you see here that in previous video, that each INSO has a many different, at least the one cell, the sensor has a two electrode, as you see here. As you see here, so that one sensor system has a 4-wire. So in a sense that if you think about the real application, especially two-dimensional application, you have a lot of the electrode, and also that requires many wire system. So instead of this layer by layer structure, we try to make that one polymer system, although it's a complex piezo, I call that complex piezo material. Then we can, using just the two electrode system, we can detect some piezoelectric as well as piezocapacitance signal, if we can have proper hybrid material. So we think about this way. The piezoelectric material, so for example, PVDF, and mixed with the polyurethane, in some case I can add some ionic liquid, then electrospin. Then during the process, some of the piezoelectric material and the piezocapacitive material doesn't like each other, although in the solution, it's going to be one common solution we can make. But during the process of the electrospinning, they're going to be microphase separated somehow. Then in the polymer material, I call the complex piezo material, has two different regions. One side is, in a sense, the piezocapacitive material. It's called polyurethane. The other one is as a polyelectric material, which is either PVDF or PLA. So if we can design very well, then we can measure both piezocapacitive as well as the piezoelectric signal, as you see here, using this kind of circuit. So from this idea, we can try that different kind of system. The one thing is just you can just make the nano web and just mechanically stack together. This is the easy way. Second method is just we try to PLA with the KHS system. But in this case, we cannot find that common solvent for both PLA and the KHS. So in this case, we use a coaxial electrospin so that we can have both solution with the one nozzle, which is a core cell type of the system, so that after all, that we have some PLA core and KHS as a cell. So we tried this second method. Third method is just PVDF and the KHS. Fortunately, we can find out the common solvent, which is a DMF acetone system, so that we can make a common, using this common solvent, we can blend together PVDF and KHS with a different composition, so that we can measure some difference between these three different types. All right, as I told you that the stacking method, you can just electrospin that nanofiber web at the different, and then we stack up and using the this two-layer system or three-layer hybrid sensor type. And the secondly, that instead of the mechanical just stacking, that then we have always some interfacial problem, so that we tried this conjective electrospinning. So also that we tried a two-layer system as well as a three-layer hybrid sensor type. And then the other two is, as I told you previously, coaxial electrospinning of KHS and the PLA. And the third one is a polymer blended electrospinning with the KHS and the PVDF, which can use a common solvent in this case. Okay, so that in that case, we can have just one layer, although the inside of the structure is slightly different. And we can measure this, compare with the three different systems. And to measuring the piezo-capacitance as well as piezoelectric, we made some tester. This is we call that the static tester to measure the piezo-capacitance using this direct drive motor that we can squeeze it and release as according to this up to 100 Newton, so that we can measure by the capacitance by using the LCR method. Another one, piezoelectric measurement. This case is the signal is in a sense faster, so we have to have a fast movement. So in this case, we use this voice coil. So it is attached to some pulse measuring load cell is attached and then press it. So this is a much faster movement. So from this system, we can measure that using the 1 gigohm load register, then amplify it, and we can collect the signal out of it. So let's see that result. As you see here that we just simply attach the KHS and the PLA nano each other. As you see here, all fibers are very similar, but in this case, with a small amount of ionic liquid, in the bottom case is a conjective electrospin system. It is, in a sense, very good performance in terms of capacitance change. This is because that normally PLA is, in a sense, a little bit brittle sample. That's why it has some creep behavior. Okay, but if we add a small amount of ionic liquid, it is somehow KHS accepting those kind of brittleness by elastic behavior. Okay. If you look at that hysteresis behavior, then it's out of this whole 5 system. Let's say with the 2 pHR included the ion liquid, that it has the best, but it's more likely about 5 to 8%. Let's move on to the second example, and the KHS with the PLA with a coaxial system. In that case, that from the PLA 100% to the KHS 100%. So from this PLA case, that capacitance change is very small because, as I told you, PLA has a little brittleness and it does not elastic. It is not elastic material. Also, it has some creep behavior. So that if you increase some KHS, and the capacitance change increase, as you see, at the 100% KHS, of course, is the best in terms of the capacitance variation. But in our purpose, maybe we can try to use some in between somehow, something like 50% of the KHS and the 50% of PLAs maybe we can use, depending on the applications. Okay, in the hysteresis is the same behavior, and the PLA, pure PLA is the worst, and the pure KHS is the best. So in that sense, that if we try to use this kind of system, somehow that in between this KHS and the PLA is somehow that we have to choose some proper value. In terms of piezoelectricity, of course, the PLA 100% is the highest signal because it is a pure PLA system. But as you increase the KHS, the signal are going to be smaller and smaller. But about 50%. So signal is about not that small. Of course, the absolute value is about 0.8 volt, but it's not that bad. So that this case, so KHS is about 50%, and 50% of PLA is, I think, one of the good choice. So that from this result, I can maybe say that a coaxial system with a PLA with a KHS, that about 50% of the KHS PLA is, I think, a good choice. So let's move on to PVDF and KH blended system. It's very similar to the previous result. So that in this case, just for the capacitance variation, that we can just look at the 50% to the pure KH case only. So as you see there, also hysteresis wise about 7 to 8%, and capacitance change is about 30 picofarad. It's not that bad. Only problem is this some kind of some creeping behavior, but we have to think about how to improve this one. So in terms of the piezoelectricity, that as I told you, that if you increase the KHS, the signal is going to be smaller and smaller, but in about 50-50 mixture, it is reasonably we can use this kind of signal to detect that piezoelectric signal. So it's the same as the PLA, although the structure is slightly different. The PLA system has the core cell type, but in this case, it's a randomly distributed the polymer system. Also, about the 50% is, I think, good enough to use this kind of system, hybrid sensing material. Okay, out of this material, we are working on that some health and wellness area, especially right now that one of project is regarding that smart shed, because the autonomous car case, you don't need any driving activity. we just need some kind of health information. So out of this kind of material, we can collect some vital sensor signal from, in the case, some emergency that we can call it. So this kind of area I'm working on, although some material is still not the best condition, in a sense that the hybrid material, the performance is just, in a sense, counterbalanced. It's one goes good and the other one is bad. But we thinking about it, how to improve this kind of thing is that adding some pesticides into some piezoelectric material, because it is, in a sense, slightly brittle. So that if we find out some kind of a plasticized material, so that then improve that the clipping behavior. Okay, this is about it. But before I'm going to finish it, that I want to say thank you to the Professor Kapchin Kim, who is an emeritus professor in Gyeonggi University. Actually, he gave me that many important instruments to do this kind of work. Also, I'd like to thank to the current moderate, Professor Anand Prabu, who is now working together with this kind of international joint project. Also, I want to thank to my former student as well as current student. Also, that my thanks go to the funding agent. Thank you.
Thank you, Professor. The one thing I notice here is like how in a Korean lab, they start with the materials and go for the fabrication and then end up with the product development. So Korea is well known for that, some academic to industry interaction. I have one or two questions from the audience. How can we improve the current output from piezoelectric polymer materials? This is one question. How can we improve the current output from piezoelectric polymer materials?
All right, good question. So that we currently that this example is just a pure component, just a PLA or PVDF. So if we add some nanomaterial, such as some barium titanate, is one example. So if we add it, then the signal is going to be actually 2 or 3 times increase. So that is one way.
Okay. Another question is, do you face any problems during the electrospinning of PLA compared to the PVDF? Electrospinning of PLA, any problems you faced?
Well, PLA case, we have a very good condition so that we don't have any problem. Okay?
Maybe in your lab, it is optimized, but if someone is going to repeat the same experiment in another lab, so they'll be facing a lot of problems. So what are the initial problems you faced while optimizing the conditions?
That's right. That's one of the important issue. But I don't know about it depending on the instrument, but if I give some, I can give you some that our condition anyway. So if he wants to know about it, okay?
Yes, Professor. And one last question is, can we compare the VPP value of PVDF and PLA? What is the peak-to-peak voltage for a PVDF sample and or for a PLA sample? What is the range of?
Well, actually, that if you compare with the PVDF and the PLA, actually PVDF is a higher signal.
Okay.
Something like at least about 3 or 4 times. So in that sense, PVDF is better, but in terms of the price, that the PLA is much, much cheaper. So that if you try to use that you require that the price of the final product is very important, then I suggest that the PLA is one of the good choice.
Okay. One general question, Professor. For example, in mechanical measurements, I will take an average of 5 readings, for example, impact strength and all. But in the case of sensor measurements, we do electrospinning, we take the sample, fabricate the sensor, and what are the data we are getting the VPP, we report that. Can you see the difference between the mechanical data and the sensor data?
Well, that the only thing you have to consider that what kind of the electrode you are using. That is also very important. That people commonly use that one of best conditions is just using that direct the metal deposition is the best. but actual real application, you cannot use it. So that in our lab, we are using the metal fabrics, which has some kind of adhesive, conductive adhesive here, so that you can use that way. But in a sense, you sacrifice a little bit about that the piezoelectric signal, but then not much.
Okay.
Okay. Only problem is that in the case of a piezo capacitive measurement, once you attach some adhesion layer on the sample, then the piezo the hysteresis increases dramatically. That one you have to consider that.
Okay. Professor, I would like to announce the participants like this. There are many questions raised. What I suggest is those questions are not read out here. You can send a mail mentioning about the speaker's name so that we will also mail you back and get the answer from the speaker. Okay, Professor. So this message is also for the participants. So thank you, Professor, for delivering this talk, and hope to see you in the VIT soon. And
I hope so.
Dean, ma'am, you want to say a few words so we can close the session? Hello.
Thank you very much for joining with us. I hope you are keeping safe, and we are expecting you to meet you again. I think there was a proposal maybe in the month of October. We have planned to meet you again. I think so, as per Anand Prabu sir schedule.
It depends. It depends on the flight schedule.
Yeah,
so situation, yes.
If the situation is all right, we will meet you again in our campus. I hope we will have a continuous collaboration in future also, and kindly support to our center by extending your your collaboration with us. Thank you so much for joining.
Thank you, Professor.
Thank you very much.
Professor.
Okay.
We'll move to the next speaker, Professor. Thank you.